So previously we have seen that sound travels through a medium or through a material medium in the form of waves, that is in the form of a wave. Now what is meant by a wave or wave motion? So this is the today's topic, wave and wave motion. But to understand wave, what is the meaning of a wave and what is the meaning of a wave motion, two simple definitions are required. So first definition is the vibration or oscillation. So vibration or oscillation, it's also called vibratory motion or oscillatory motion. Roughly, it is also called as vibratory motion or oscillatory motion. What is this vibratory motion or oscillatory motion? In simple words, vibratory motion means the to and fro motion of a body. To and fro. To and fro means to means something like towards a particular direction, say rightwards. Fro means away from the direction, away from the particular point. So towards a point and then away from the point. Towards a point, observe the cursor compulsorily. So towards the point and away from the point. So it's called to and fro. So such a to and fro motion roughly is called as vibratory motion or oscillatory motion. Sometimes it's called vibratory motion, sometimes it's called oscillatory motion. Now there is a slight difference, small difference between vibratory and oscillatory motion. Oscillatory motion means usually slow to and fro motion. Vibratory motion means faster to and fro motion. So it can be understood from a simple example. Now this is the example of vibratory motion. Now from this the exact meaning of vibration and oscillation can be obtained. So now consider a spring. Now this is a spring, an ordinary spring, just like that. So this is the regular spring. Now the top end of this spring is actually fixed to a rigid support like a wall, and the bottom end. So the diagram is actually a fully completed diagram I have drawn, because this is a diagram actually which will be actually helpful. So which has to be drawn in the notebook. For example, this particular topic you are writing notes also, then this is the diagram, and even supposing it's you have to draw it in the exam, this way it should be drawn. So because it's a little too many details are there in the diagram, I'm drawing it separately. So this is the spring, the top end of the spring and the bottom end of the spring. So top end is actually tied to rigid support like this, and at the bottom end a load is attached. A load can be imagined to be a small stone like this, but stone will be a little heavy. So best way of imagining the load is a wooden load, which will be very light. Or even for convenience, if you want, you can imagine a stone also, because it has stone means it will be slightly heavy. So it doesn't matter. So any load which is actually suspended to it. So if it is a stone, it's because of its slight heaviness, the spring will be slightly elongating. So in order to avoid that, a wooden load, if it is suspended, the spring, because wood is too light, the spring elongation will be negligible. So almost it will be in its natural length. For that reason, I am telling that a wooden load can be imagined also. So now initially this particular load, imagining that it's a very light load, that means the spring will not be extending much. Its extension is negligible because of the weight or heaviness of the load. So initially the load is at its position of rest, initial position of rest. This is called as mean position. This is called mean position. Mean position. These words, terms, terminology is very important. So the initial position of rest is called as mean position. It's denoted as O. This initial position, the center of the load, is denoted as O. Now from this initial rest position or mean position, you pull the load downwards this way to a small distance. This final position, it's called extreme position. This is the mean position, and this is called as extreme position in the downward direction. So you call it as y dash. So to this position, you are pulling the load down and then leave it. Once you leave it, because the spring got extended, because of the elastic nature of the spring tries to go back to its original length. So in the process, the spring will pull the load upwards. This particular load will be pulled upwards. So by the time it reaches the initial position, it will be picking up a large velocity because of the elastic force, upward elastic force applied by the spring. It will be it will be gaining a large speed, a high speed or velocity. Because of that speed, it will not stop here. Because of inertia of motion, it continues to move further. So as the load continues to move further, now the best way to imagine, now when the load is moving further because of inertia of the stone or inertia of the load, now its stone will be easier to imagine now, because of the stone being heavier, mass being greater. its inertia will be greater. Mass is a measure of inertia. That is what you have learned in motion and also the laws of motion. So because it's picking up a high speed, by the time it reaches from the extreme downward extreme position to the mean position, because of that high speed it continues to move further, and now as it moves further it will compress the spring from its this is the natural position, natural length of the spring up to here. So because of the high speed of the load, as it moves further, the spring will get compressed. As the spring gets compressed, you can just observe that it becomes slower. It will be slowed down as the spring gets compressed. So finally the load will be stopping at position Y. So this is the topmost position. This is called top extreme position. Top extreme. Extreme means end position. This is the top end and this is the bottom end of the motion of the load here. So firstly we have pulled it down to the bottom extreme position. Extreme position means end position Y dash. And when we leave it here, it moves towards the mean position with a high speed. It will move because of the elastic force. This elastic force is sometimes called restoring force. It is also called as restoring force. So more simpler name is elastic force. So because of its high speed acquired here, it continues to move further, now compressing the spring. Because as the spring gets compressed, its motion will be the slowed down, and finally the load will be stopping at the top extreme position Y. So this will be the top extreme position of the load. It's shown by a dotted diagram, a dashed diagram. The actual original position of the load is shown by a thick line here. So this bottom extreme position is shown by a dashed line, and the top extreme position also is shown by a dashed line. So this is the top extreme position, the center of the load. So this path along which it has moved, the stone has moved, the load has moved first downwards and then upwards, is shown as Y dash. So the path is not visible here, that's why it's shown separately. This path is very important for understanding vibratory motion or oscillatory motion. Now as the spring from the state of compression, the spring will push the load down. So by the time the load moves down to its original position, again it will acquire a high speed. Again, because of inertia of motion, it will not stop at this mean position. It will further move downwards. So this way it will be moving downwards, upwards. So from the initial position, that is from the top position, if we take, or even if we take the bottom position, from the bottom position it's actually moving upwards towards the top position, and then again away from the top position. So towards, to, and observe the words to and fro. To means something like towards. From the bottom position it's moving towards the top position, towards, and then from the top position it's moving away from. Fro means something like from, away from, it's moving towards and then away from. So this to and fro motion itself is called as oscillatory motion. So most important thing for to and fro motion here is elastic force should be there. So what is applying the elastic force? Act on the body, on the stone, on the load, the elastic force applied by the spring. That is very important for vibratory motion to occur. So if this vibratory motion is very fast, it's called, if this to and fro motion is very fast, it's called vibratory motion. And if this to and fro motion is slowly, it's taking place like a pendulum, it's taking place slowly. When the load is very heavy, this happens slowly, it will take place. When the load is very light, fast, it will take place, then it's called vibratory motion. Now the meaning can be seen clearly, more clearly, the difference between vibratory and oscillatory motion. But usually we consider not too fast and not too slow, so medium. So roughly both of them are taken to be almost same, vibratory motion and oscillatory motion. So thus we have the complete meaning of the vibratory and oscillatory motion. So what is the definition of vibratory and oscillatory motion? The definition is very simple. To and fro motion of a body due to an elastic force acting on the body itself is called as vibratory motion or oscillatory motion. Now consider this vibratory motion. Now the exact meaning of vibration or oscillation. What is the meaning of one vibration or one oscillation? It can be understood like this. What is one vibration? One complete to and fro motion is called as one oscillation. So it's simply called as one vibration or simply one oscillation. This term is also very important. Terminology is very important here. So always in science and technology, terminology plays a very important role. Every term has an exact definition. Exactly it has been defined. So how one vibration is defined? So now earlier we have seen vibratory motion and oscillatory motion. To and fro motion due to an elastic force is vibratory and oscillatory motion. Now what is one vibration? One complete to and fro motion. So for example, from down to up it's moving, and again that is towards the uppermost point, and then away from the uppermost point, that is towards downwards it's moving. So this one complete to and fro motion is called as one vibration or one oscillation. The important thing is this is taking place due to an elastic force. That is very important. Or elastic force, sometimes called as restoring force also. So that is also included in the definition of one vibration or oscillation. Now, so thus in this from this simple diagram itself, we got two definitions. One is vibratory and oscillatory motion. Next, what is one complete vibration and one complete oscillation. So from this, we're getting another very simple definition, the definition of time period. So before that, just one sec. So here, vibration or oscillation, it's a very important definition. So carrying about 2 marks for almost all the boards, whether it is central board or different state boards, it carries roughly about 2 marks. Just a simple definition. Supposing explanation is also, supposing it's given for 3 marks, a little explanation also can be written. So in the explanation, the diagram actually will be coming. Otherwise, just for definition, 2 marks, just a definition is sufficient. Supposing it's given for 3 marks, then explanation along with the diagram can be written. So here, important thing is mostly it's given for 2 marks. So just only definition is sufficient. So diagram and explanation, all that will not be required. So later I'll directly display the, so at the end of the class, directly I'll display the definition, written notes directly. Whatever I have explained in the same words, I'll give everything as it is. Whatever definition we have seen in this, exactly in the same words, not even little change also will not be there. Even little change also will not be there. Now what is time period? So it's simple, directly it can be understood like this. The time taken for one vibration. So what is one vibration? Already we know. So from the bottom, supposing it's starting in the vibratory motion, so towards the top point once it is going, and then away from the top point it's going down completely once. So this one complete upward motion, that is towards the top point, and one complete downward motion, that is away from the top point, this is one vibration. So whatever time it takes for this one vibration is called as a time period. So this is very important definition, but compulsorily it requires the understanding of one vibration or one oscillation, or simply the definition of one vibration. So see here, the definition of one vibration or one oscillation, simply it's also called definition of vibration or oscillation. That's compulsory required for understanding the definition of time period. So this is also another very important question, but it's very simple to answer. The what is the meaning of vibration or oscillation is understood. From that we can easily get this meaning of time period. It doesn't take much time. So as we can see here, the time taken for one complete vibration or oscillation is called as time period. So what is one complete vibration? One complete to and fro motion towards the top point, from the bottommost point towards the top point, and then away from the top point again back to the original position. We are imagining that the body is starting from the bottommost point, so it should go completely upwards once and then again return back to the downward point position again, or downward extreme position again. So that is one complete vibration. So whatever time it takes for this one complete vibration is called as time period. So what are the units of time? So units of time we know already, very simple. The SI unit or MKS unit of time is a second. So symbol for the unit of time is what? S. So that's about the definition of the time period. So now from based on these two quantities, very easily the meaning of wave and wave motion, that is the definition of wave and wave motion, can be understood. What is the definition of a wave? So what is the meaning of wave and wave motion? Now this can be understood from a very simple example or from a very simple diagram. I'll just we'll just go to the diagram. It's a very simple diagram. Now this is the diagram. So I'm just putting the side heading once again. So actually it was on the right hand side of the board. So I just moved it to the left hand side of the board so that the diagram will be visible on the right hand side, because from the side heading we are going to the example or diagram which actually explains the meaning of wave and wave motion. Now what is the meaning of wave or wave motion? Now it can be understood from this example. Now consider a rope or a string. Now this is a rope or a string. Now right end of the rope is actually fixed to a wall. Now this is a wall. This fixed line is a wall. So the right end of the string is fixed to the wall. Now imagine that the string is slightly heavy string, slightly heavy, just like an ordinary rope, and the left end is free. So this string has its own weight. So that's easy to imagine, like a ordinary rope, a rope which is used for say tying so books, etc. Tying books, a bundle of books. Such a rope we are imagining. So right end is actually suspended or fixed to the wall, and the left end is free to move. Now this left end of the string, now the first most particle at the left end, the first particle is known as 1. Like that, a second particle can be considered, third particle, fourth, fifth particle, different particles can be considered. So the first particle actually now, which is on the left hand side of the string, let the string be held in the hand, and then immediately let the string be lifted up, and then immediately down back to the same point. Now this initial position of the first particle is known as O. It is denoted as O. So now what we are doing is we are disturbing the string at the left end. So we are just holding the left end of the string, the particle 1 we are just holding, and we are giving the string a jerk. We are just moving it up to the position Y, and then we are immediately moving it down again back to the same position. This is an upward jerk. This is simply called as upward jerk. I'm moving it up and quickly bring it back again down to the same point. This is an upward jerk. Now here the path, you see the path taken by this particle from O to Y it is moving, and then Y to capital Y here. Just observe here, capital Y back to O it is moving again. So this is called as an upward jerk. It just moved like this. Just observe here. It just moved like this, and then again back to the same point it's moved. So it's just moved upwards like this, and then back to the same point it's moved like this. It's given an upward jerk with the hand by holding the this free end of the string. This end, one particle 1 or the left end of the string is called free end because it's free to move, but the right end is fixed end because it's fixed to the wall, it can't move. So this free end, when it's given a jerk, that means the string, holding the string at its left end, we are jerking the string. That means we are jerking the left end of the string. We are just moving it up and again back to the same position we are moving it. Now this is somewhat similar to vibration, you see. Already we have seen that the meaning of vibration. Just see here, this was the meaning of vibration. So what is vibration? We are taking a initial position of the object, load is O. So this we are moving it down, the load we are moving it down to the position Y dash, and then we are leaving the load here. It's going up back to the original position, mean position O. Mean position is can also be called a central position because it's present at the center of this path Y dash. So here the object, the stone or load which is coming to here, once we leave the stone or load here at this position Y dash, after stretching the spring, when we leave it here, it will go to the position O, and because of its high velocity it goes further compressing the spring, and slowly as it goes up the spring gets compressed, due to which it will slow down, the load will slow down and finally stops here, stops at Y. This is what we have seen earlier in the meaning of oscillation or vibration. Just try to remember this while learning the definition of vibration or oscillation. We have seen this example, this particular example. So once the load comes to rest at position Y, Y is called as top extreme position, Y dash is called as bottom extreme position, O is called as mean position, which can also be called as central position because it's in the middle of the path. It's in exactly at the center of the path Y dash. So once it stops here, again it will be further pushed down. So again it will be moving down, and from here it will move down further to Y dash. This way it executes vibratory motion along the path Y dash. This vibratory motion will present equally. The motion will be almost identical above the mean position O and also below the mean position O. So this upward motion, once it's during vibratory motion, there are two directions of motion. Once upwards from Y dash to Y, Y dash to O to Y, that is Y dash O Y upwards, and then downwards Y dash. This way it's executing to and fro motion. Upwards is towards the topmost point Y, and downwards is away from the topmost point Y. So to and fro motion itself is called as vibratory motion. Now just here one small thing is this total time taken for this one vibration, that means upwards, complete upwards motion from y dash to y, and then complete downward motion from y to y dash. This one complete to and fro motion itself is called as vibration, and the time taken for this is called as time period. Its symbol is denoted as t. This is very important symbol. Capital T denotes the symbol for time period. This is what we have seen earlier. Now just observe here, this is the mean position. Now when it is going, so as it is going upwards, now again consider the same thing. As it is going upwards, so from the mean position, supposing it goes to the extreme top extreme position, and from there again it's going down back to the mean position. So all the while when it is going from mean position, during its upward motion, we are considering this as the load is actually moving from y dash to y. Imagine the mean position O. So from here how it is going, it's going upwards. So this total length is say, yy dash, means above the mean position the length will be about half of this yy dash length. Imagine that yy dash length is some l, means above o to y this will be l by 2, and below o to y dash will be the next half l by 2. So whenever the motion of the load is in the upper half, supposing it's going from o to y and then back to o, this is completely in the upper half of the path. That's why this is called as upper half of the vibration. What is upper half of the vibration? From O to Y and back to O. This is complete upper half of the vibration. And then when supposing that during its downward motion, when the load is moving downwards, so it will from O to Y dash it will go down, and from Y dash it will again go upwards. So all the while as it goes from O to Y dash and from Y dash back to O, this now completely the motion is at all positions of the load. Where is the load? It is below O. That means in the lower half of the total distance L or total length L, the motion is actually taking place. So this particular motion from O to Y dash, just observe carefully, it's not difficult. So when the load is moving from O to Y dash during its vibratory motion, now already we know how the vibratory motion takes place. The best way to imagine the vibratory motion is complete upward motion y dash to y, and then from y to y dash. This one complete upward motion and one complete downward motion together, it's called as what? One vibration or one oscillation. So this itself is defined as one vibration or one oscillation. Now in this, now we are again dividing this one vibration into two different halves. One is above the mean position O and one is below the mean position O. So when it is going from the mean position to top extreme position Y and then back to O, the motion is completely in the upper half of the path. So that's why it's called as upper half of the vibration. Just remember this, upper half of the vibration. And when it is moving from the mean position O during its motion, continuous motion, at one point it will be at O. When it is at O, and as it starts moving downwards, it goes to the bottom extreme position and then again comes back here. This all this while from O to Y dash and Y dash to O, the motion is completely in the lower half of this total length L. So this is called as lower half of the vibration. Always total vibration, one vibration takes place what? One vibration, how much time it takes? One vibration means it takes a time period T. Time taken is called as time period T. Half vibration means it will be taking exactly half of the time. For example, from bottom to top, how much time it takes? Exactly, you can guess that it's half the time. Bottom to top and top to bottom, total time is one vibration time. It's nothing but time period. So only bottom to top means exactly bottom to top. Y dash to Y means time taken will be, easily we can guess that it will be T by 2, half of the total time period. Total time period means bottom to top and top to bottom. This total time. Only bottom to top means it will be half of the total time, T by 2. And again from top to bottom also it will be half of the time period. So bottom to top is called as half time period. That's called half vibration. And the same way from top to bottom is the next half of the vibration. The same way we can also get this half vibration can be also. Another thing about the half vibration is full vibration. One full vibration time taken is time period. Half vibration time taken will be T by 2. This T by 2 is actually very important. It's also very important, as useful as the time period T. So now if you take the upper half of the vibration also. So what is the upper half of the vibration? Just once again see, from the mean position O, it's going to the top extreme position, and from the top extreme position again back to the mean position O. This complete motion is taking place only above the O. Complete motion is taking place above the point O. That's why this is called as upper half of the vibration. And from O, when it's going downwards, when does it go downwards? During its downward motion or downward half of the vibration. So y to y dash is what? Downward half of the vibration. During this downward half of the vibration, what is happening is from the mean position O, firstly it's going down to the bottom extreme position, and from bottom extreme position y dash it's again returning back to the mean position O. So this entire motion is below the mean position. So this, for convenience, exactly it's called as, because it's taking place only in the lower half of the vibratory motion path. Vibratory motion path is what? L or y o y dash. It's taking place exactly in the lower half, L by 2 it's taking. That's why it's called as, it is also called as lower half of the vibration. So upper half of the vibration, lower half of the vibration always take what time? T by 2 and T by 2. So total vibration will be what? T, that way. So any doubt is there, just think of this example, very easily it can be understood. So now come back here. So any doubt is there, just think, just put the video to a pause here and think on your own. Very easily any doubt can be clarified. Always understanding will be possible only by looking at the real life situation, real life example. So real life example, experimental setup will be very difficult. Putting a spring and putting a load which is not too heavy, not too light, exact load, convenient load should be placed, and very carefully the experiment will be done. All this will be taking a lot of time, and this entire effort can be minimized very easily. It is possible to observe what is happening just by looking at the diagram. So this is the power of a simple diagram. So it's almost as good as the real experiment. Just by looking at the diagram, everything can be understood very easily. So any doubt is there, just look at this diagram. Very easily the doubt can be clarified. Put the video to a pause and then just look at the diagram. Very easily, whatever doubt is there in the mind, it can be easily clarified. So now come back here. So this left end of the string, the particle is the first particle of the string, it's called as 1. So initially it's at its own original position. So it's simply called as initial position of rest. So above this position of rest O, we are just giving this left end of the string a jerk. First we are moving it from this initial position to the topmost position Y, and then again bringing back here, back to the same position. So all these points from O to Y and Y to O is nothing but what? Imagining the path y over dash, O to Y and Y to O is what? Upper half of the vibration. Now below O there is another lower half of the vibration. So that is also possible. So such a point exactly at some distance Y above O, we have considered the top extreme position. A similar bottom extreme position Y dash also can be imagined, but this Y dash will not be useful now. But just imagine that we are considering a similar path Y over dash here, exactly here, for this particle also to vibrate. But now we are considering only the upper half of the vibration, because we are giving the left end of the string, the particle on only an upwards jerk we are giving. Jerk means we are just lifting it suddenly upwards and then back to the same point downwards. That is what is happening. So there is no complication here. It is not difficult to understand. So for example, when we are giving it an upward jerk, what will be the shape of the string? It will go like this. The string will become like this. So only for convenience I am drawing. Actually this is not required. I'll just remove it also, this immediately. We are giving, first we are suddenly moving it upwards, this particle 1 from the initial position O, we are moving it up to point Y, and then again we are moving it back to point, the same position O we are moving it, this particle. So this itself is called as upward jerk or upper half upward jerk. So once it is going upwards and then back to the same point. So this way it's jerked. So from the initial position O to the top position Y and then back to the same point O. That way the particle is given an upward jerk. So this is nothing but upper half of the vibration, because it's above the initial position. Initial position is nothing but called as what? Mean position or central position also during vibratory motion. Such a vibratory motion can produce here also. Now the same thing can be done even for the particle if it's given a downward jerk also, but downward jerk will be exactly similar, not difficult. So when it's given upward jerk, once it is moved from O to top extreme position Y, the shape of the string will become like this. And again when we move it back again, the particle 1 from Y, it comes back to O. Instead of giving this upward jerk, we can give it a downward jerk also this way. The particle 1 can be moved down like this and then again moved back again to the point O again. So that's called as a downward jerk. During the downward jerk, when the particle 1 is moved down, the shape of the string will become like this. But all that is not important. Again, when you move it back again, we are completing a downward jerk, or lower half of the vibration also we are considering. So any doubt here? So just put the video to pause and think on your own. No complication is there. So this is a real life example. There's not much difficult. Any difficulty is there? Take your own time. Understand the situation. It's not difficult to understand. So now I'm removing all this. So this shape of the string, I'm just removing it so that we'll come back to the original diagram. So now we are just giving it an upward jerk. So when it's given an upward jerk, what really happens is, so we are just moving it up, and then left end of the string, the particle one, we are lifting the string upwards. So the shape of the string becomes somewhat like this, curved upwards. This way it will be somewhat curved. This way it will be curved. And then when we bring the string back again, what happens is a disturbance will be formed here. A disturbance will be, the shape of the string will be somewhat like this. So this way it will become. So don't bother about the brown arrows here. Some one brown arrow is shown. This brown arrow denotes that in what direction the particle is actually moving. So at time t is equal to 0, we are starting this experiment. We are starting the particle 1. We are making the particle 1 to move upwards at time t is equal to 0. So this is the initial time. Initial time usually is taken as 0 time only. That's why at time t is equal to 0, the particle starts moving up. So brown arrow denotes the motion of the particle. This is very, very useful, but now it's not required. Later this becomes very, very helpful, brown arrows. So we'll come back to this again. It will be very important. Even in the other diagrams also brown arrows are shown. They also will be very, very useful. But now the important thing is when the upward jerk is completed, or upper half of the vibration of the particle 1 is completed, O to Y and back from Y to O. So above the mean position from O to Y and back from Y to O. What is this now? Upper half of the vibration, because taking place only in the upper half of the length of the path Y over as denoted as L. So when this is completed, what happens is the shape of the string will be disturbed up to small distance. So up to a small distance, the particle at the end of this distance is known as particle 2. So then the shape of the string, because of this disturbance that is created in the near the left end of the string, the shape of the string will become somewhat like this. This shape is called as convex shape. Convex shape means what? This shape, curved upwards. What is concave shape? This is called as concave shape. So because we have given an upward jerk, we moved it up and then back, we just moved the string this way, and then back we are moving it like this immediately. So due to this reason, what happens is the shape of the string will become like this up to a small distance. This way it will become. So this is what is happening. This kind of convex disturbance that is created is called as a crest. It is simply called as a crest. So that's the important. So that's the shape of the disturbance that is created here. So this disturbance, which is actually present in near the left end of the string, is actually present through for a small distance. It's present from particle 1 to another particle. This other particle up to which the disturbance is actually present. Disturbance is present means the string is actually getting disturbed. Is called as particle 2. So beyond this particle 2, the string is still undisturbed, just as in the original situation. So that is how we are getting the upward disturbance, or we are creating an upward disturbance in the string, which is simply called as crest. So now what is the time taken for this? So how much time how much time it took for giving the upward jerk to the left end of the string, or the left end of the string, which is known as 1 here. How much time it's taken? So from O initial position to the topmost position Y, and then back to the initial position. So this is nothing but upper half of the vibration. It is nothing but upper half of the vibration. So still we did not go to the lower half of the vibration. Just the particle is again brought back to the mean position O. This particle 1 moved to Y, and then from Y to back to O. It's moved. So at this instant, what is happening? The time taken for this upward motion O to Y, and then from Y to O, it's taking place entirely in the upper half of the path Y O Y dash. So this path Y O Y dash is what? L. Upper half means upper L by 2. So what is the time taken, total time taken for this? Already we have seen that it is nothing but half the time period. T is equal to T by 2. So this is how the situation is present. Now we can just easily understand, just here a downward arrow. So here this particle at time t is equal to 0, it was actually just starting to move upwards. Now because it has completed already at time t is equal to 2, half vibration it has completed. From O to Y it has moved, and again from Y to O it has moved again back to O. But it's now moving in what direction? Downward direction. It has come to O back again in the downward direction. That's why the brown arrow is shown here. So that's the importance of this brown arrow. That like that in the diagram, whatever is the direction of the particle, that is moving particle or vibrating particle, that is actually shown by the brown arrows. Even this brown arrow also has its own meaning. So this also can be understood. This meaning of this brown arrow upwards can be understood only from the definition of wave. It can be understood from the definition of wave. So what this wave definition now can be easily understood by considering what happens to this disturbance, which is simply called as crest. Now the important thing is this crest, it is found that once the crest or this particular convex disturbance is formed in the string, it is found that immediately it starts moving along the string with a definite speed or velocity. Immediately it will start moving along the string. Now remaining part of this string, you see, from particle 2 up to the right end of the string, it is completely undisturbed. But what happens is a little later, this disturbance, whatever disturbance that is got created here, it immediately starts moving along the string towards the other end. This way it starts moving with a definite velocity. Crest actually starts moving. So at any time greater than t by 2, where will be the crest? Means it will not be here, because it starts moving with a definite velocity. It will be occupying a new position. It will not be here. It will be reaching somewhere here between 4 and 5 or between 5 and 6. Anywhere it can be present depending upon how much time we are giving it. We are giving more time means it travels more distance. Less time is less distance, because it's traveling with a, it is found to travel with a fixed or constant velocity. So how the diagram will be looking like? The diagram exactly looks like this. Now the important thing is we gave the string, left end of the string, that is the particle one, only an upward jerk we have given. We just move it up and then back to the same position. After that, the string is not disturbed. Imagine that beyond the time t by 2, the string is not disturbed. It means the particle one is kept like that. We are just holding the particle as it is. At the same point only we are holding it. We are not giving it any more jerks. But once the disturbance already got created here, it will not be staying there. Immediately it starts moving, and the diagram will become like this. So this way it will become. Just observe here. This is a very, 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 very important thing in understanding wave. It looks like this. This is what happens. This is the exact diagram after need time greater than t by 2. So earlier, where was the crest or disturbance? It was here. But any time greater than t by 2, because it starts moving with a velocity, constant velocity v, it moves to some other new position. It goes. We allow more time means we have given a certain time for this to move forward, means it has reached here, say. We'll give it still more time, it goes like this way. But the remaining portion of the string where the disturbance has not yet reached, still it will be remaining undisturbed. And what about the left hand side? Left hand side is also coming back to its original condition. Originally it was, how was the left hand side? Just observe here. So this is very, very important. Originally, how was the entire string? It was entirely undisturbed. Once we disturbed it, the particle one, for a time of taken how much time we have disturbed it? T by 2. Exactly half time period, exactly half vibration, upper half of the vibration. We made the particle 1 to undergo upper half of the vibration. Then a crest got formed, upward disturbance, a convex disturbance got formed, and that it is found that it starts moving. Why it starts moving is not difficult to understand. It can be understood very easily also. But now the important thing, most important thing here is, which actually leads to the definition of wave or wave motion, is the crest starts moving, the disturbance starts moving along the string or along this medium. So the string through which the disturbance is moving is also called as medium, which is actually helping the disturbance to move. If there is no string here, the disturbance will not be moving. So string is present here. Along the string, the disturbance starts moving. So along this string or along this medium, the disturbance starts moving with a definite velocity. So as the disturbance moves further and further, what is happening is, wherever the disturbance goes, the shape of the string really becomes like that. For example, what is the disturbance here? Really, it's nothing but string itself. The shape of the string becomes like this. Really, it becomes like this. So when the disturbance comes here, the shape of the string here, it has become convex like this. So wherever the disturbance goes, there the same shape of the same exactly identical or same shape of the string is formed. Remaining portion will be still undisturbed. Even on the left hand side also, it comes back to the original undisturbed condition. This is how the disturbance is moving. Now why? The important thing is, Now many of you have guessed it. What is the disturbance which is moving this way steadily, very very smoothly? It will be moving. What is this disturbance called as? This itself, this disturbance which is moving steadily with a constant velocity or constant speed itself is called as wave. And the motion of this wave itself is called as, or the motion of this disturbance itself is called as wave motion. So rough meaning, now we got the meaning of wave and wave motion. Now the important main question is how the disturbance moves from this end to the other end. Now this is not difficult to understand, but it is simple itself to understand this also, reason for this, but it is very very important for understanding how the wave is actually traveling, how the disturbance is actually traveling. Now the disturbance, what is the other name for this disturbance which is moving? Other name is the wave itself. How the wave is actually traveling? The wave is traveling simply because we are actually holding only the left hand particle of the string. Only particle one we are holding. Say with two fingers, we are holding it. With between two fingers we are holding it. Only particle one only is in our hands, or between the two fingers we are holding. So remaining string we are not exactly holding. But particle one, when we are vibrating it, particle one is actually connected to the next particle. Next particle you call it as 1 dash, because this far away particle we are calling it as 2 for convenience. So, but the particles will be continuously present. After particle one, immediate next particle will be there. It can be called as 2 dash. Next particle 3 dash, 4 dash. We are not using the same numbers because we are using certain 1, 2, 3, 4, 5 for special particles, which are very very important for understanding of the wave motion. So beyond particle, after particle 1 on the right hand side is particle 2 dash, 3 dash, like that continuously. So when we are vibrating the particle 1 is connected to the next particle. So whatever vibration we are giving, whatever way we are making the particle 1 to move, a little later, next particle also will be forced to move the same way. So next particle, after the second particle, after beyond 1, after the second particle 2 dash, the 2 dash is in contact with the third particle. So the same vibration will be transmitted to the third particle 3 dash. But a little later, a little later. This will continue from law of conservation of energy if there are no energy losses. Energy means what is the energy that is given, which we are giving to the particle due to motion? It's nothing but kinetic energy. So from law of conservation of energy, this kinetic energy should remain constant. So whatever kinetic energy we are giving, that should remain constant because of law of conservation of energy. We are mainly considering kinetic energy here. So the next particle will force to vibrate. So first particle we are disturbing it, we are making it to undergo upper half of the vibration O to Y and back from Y to O. So that will force the next particle, its neighboring particle to vibrate. The next particle will again force the next particle to vibrate. One forces 2 dash to vibrate, 2 dash forces 3 dash to vibrate, 3 dash forces 4 dash to vibrate. So this way, one after the other, without any loss of kinetic energy or loss of energy. So law of conservation of energy states that total energy remains constant. So here the total energy of the particle will remain. The total energy which we are giving is remaining constant. To which particle we are giving? 1. So 1 gives energy to next particle 2 dash. Like 2 dash will give 3 dash. Like that the energy will be transmitted, or vibrations will be transmitted from particle to particle. So this has to continue from law of conservation of energy. Energy will never be getting destroyed. So this transmission of energy will continue till the last particle at the right end of the string is reached. So we know that definitely the disturbance has to continue this way due to transmission of vibrations from one particle to the next particle continuously till this continues to the last particle. How this disturbance looks like means, definitely we know that disturbance will be transmitted or vibrations will be transmitted from one particle to other particle. How it looks like means, it looks like this way exactly. So in from real life example, we can say that the disturbance will be moving like this. So have we seen this particular example anywhere else? So in real life also we have seen this easily. Many of you might have done this experiment some way or the other while playing, say, using ropes. Doing such a similar experiment, many of you might have observed this roughly. Now more clearly this can be just remembered, and many of you have seen this in similar situations also. What is that one similar situation? I'll just show. It's a very simple situation. Just observe this here. This is a situation, a bed sheet. Just see here. Now this is a bed sheet. It's a rectangular bed sheet like this way. Just an ordinary bed sheet like this. This is AB. This is say PQ. This is a left side PQ. This can be taken as AB. Actually, here in the actual diagram, it's shown as A and B. So I have written it as so it doesn't matter. Anyway, it can be taken, for example, or else I'll just use the same representation. So right side is denoted as AB. Left side is of the rectangular blanket or bed sheet is denoted as PQ. Now let this be fixed. How it is fixed? One person is holding both the ends, both the corners A and B fixed, so that they will not disturb. Now, supposing you are holding the left side, so in the two hands, the two corners P and Q you are holding it. Now give it an upward jerk like this. Once you move it upwards and then immediately move it downwards at the same time. So you are just giving it an upward jerk. The same situation as we have seen earlier. We are just giving it an upward jerk. Just observe here. So first we are moving it upwards and then immediately downwards this way. Suddenly you are moving the left side PQ upwards and then immediately moving it downwards this way. Just see here. First you are moving it up and then immediately down. Immediately an upward disturbance will be getting created. So you're jerking it like this. First suddenly like this and then immediately downwards like this. You are holding it at these 2 points. Left hand you are holding at corner P, right hand you are holding at corner Q. Give it an upward jerk. Immediately you know that an upward disturbance gets created. So it will be spreading up to small distance like this from here to here. So you can just imagine this here. Exactly like the rope here. Just here, same rope. Upward jerk you are giving it. So upward jerk. So this way its shape will become the same way it will be formed here. So this is nothing but a crust. Then you observe this. Many almost everybody can now you have done this when you are dusting the bed sheet. You might have done this. You can just remember at least to some extent. Today you just repeat this experiment very easily. You can just prove that the upward disturbance crest which got created here immediately starts moving with a definite velocity towards the other end. So once this continues till it reaches the other end. So this is nothing but what? A wave. This special motion of the disturbance is called as a wave. But how this wave is propagating, just observe here. How this wave is propagating, or propagating means traveling. How the wave is traveling? Because of transmission of vibrations. One particle, its own vibration is transmitting to the next particle transmitting the vibration to the next particle because of vibrations of the continuous transmission of vibrations. So even if one particle is stopped from vibrating, for example, with two fingers you hold the string here at this point, you don't allow it to vibrate here at this particular point. Just observe here you stop the particle from vibrating. Then what happens is the wave will not go beyond this point. Without vibrations of particles, wave traveling is never possible. Wave is never possible. You just hold the string here at this point, immediately the wave will be stopped here. It can't go beyond this. So actually it can prove that it get reflected also. Waves can get reflected. You already learned light waves get reflected. Sound waves also actually get reflected. All waves get reflected. So if you hold the string here, not allowing it to vibrate the particle, then the wave will be stopped here, and after stopping here it will get reflected just like a regular ordinary elastic object gets reflected. The same way it get reflected. So but it can't propagate further. So for wave propagation, very important thing is, I'm just removing this point just here so that the diagram becomes original diagram. So once the string is stopped from vibrating, we are not allowing it to vibrate, there the wave will not be further progressing. Beyond this no wave will be present. So compulsorily vibratory motion is required, without which a wave cannot propagate. Only because of vibrations of the particles of the string, the wave will be propagating. So we got only upward disturbance because we have considered only upper half of the vibration. The same way, if you consider lower half of the vibration, what happens is a lower downward disturbance will be getting formed. The downward disturbance is called as trough. So here we don't have. So actually, in the next diagram, a trough is also shown here, but will immediately it will be like this below. I'll just move it down a little later. But now we'll see this. We can understand it from the same diagram. We can also understand trough also. But how trough is formed? By making the particle want to vibrate, complete the lower half of the vibration. But that is, we have to give the left end of the string a downward jerk. That is from O to Y dash to O. So then we can just easily imagine that a downward disturbance, that is a concave downward loop or downward disturbance gets formed. That itself is nothing but a trough. Even the trough also will start moving along the string, because again of the transmission of vibrations from law of conservation of energy. So that's how The second type of disturbance also can move. A trough also can move along the string. Now there is no complication here. Everything, whatever example we have seen is very simple. Though it's taking some considerable time, it is not difficult to understand. There is no complication here. Even a trough also can be understood here. So there's at the end of time t is equal to t by 2. That is half time period. That means half upper half of the vibration is completed. That is the end of the string is just given an upward jerk. So the left end of the string is just moved upwards from position O to position Y, and then back to point O again it's moved. So it is upper half of the vibration is completed, or simply upward jerk is given to the string. Then we have seen that an upward disturbance, that is a crest got formed. A crest gets formed, and this crest immediately after its formation, it starts moving along the string because of transmission of vibrations from one particle, from the first particle to the last particle. This continues. First particle, next immediately next connected to the first particle is the next particle. Next particle is connected to the next particle. Like that continuously they are connected to each other. This disturbance automatically the vibration which is actually given to the first particle is actually transmitted. So the disturbance, the string gets gradually disturbed from particle to the particle. So disturbance definitely in some form it will be reaching here. We know that easily, we can guess that. And how it looks like means it looks like exactly like this. The crust continuously, smoothly, very very smoothly it moves along the string from the left end to the right end. So this motion, this disturbance or crest which is moving along the string itself is called as wave, and this motion itself is called as wave motion. Now the most important thing about wave motion is definitely the wave or crest here, the wave is in the form of a crest, or the disturbance is in the form of a crest. It's actually moving along the string due to the vibrations of particles, that is due to transmission of vibration from one particle to the other particle. That is a very very important thing related to the wave motion. Now just observe how each particle is actually vibrating. Now, how is each particle vibrating? So this is also very, very, very important point related to wave or the wave motion, from which only actually really will get the definition or complete definition of wave motion. Already we have seen the rough meaning of wave and wave motion, or rough meaning of what is called as the disturbance which is moving, which actually is, itself is called as wave, and the motion of this disturbance or motion of this wave is called as wave motion. So another very very important thing is related to the vibration of each particle. We already have seen that for the wave to propagate or for the disturbance to propagate along the string, compulsory vibration of particles is required. Any particle not allowed to vibrate, immediately the wave stops there, and it can't propagate further beyond that point which is not allowed to vibrate. So vibration is compulsory for wave motion. It's compulsory for wave motion. That is what we can get from this particular example, or from this particular observation. Strictly speaking, from this particular observation we can easily say that vibration is required. No vibration, no wave propagation, no wave existence. So now how is each particle vibrate? That's the next important thing. Already we have seen that the first particle 1, which is really the present at the left end of the string, is only completing the upper half of the vibration. So start here at time t is equal to 0, the particle 1 starts moving upwards from the mean position O. Then during the upward jerk of the left end of the string, the particle from O to Y it moves, and then from Y back to O. So this is only upper half of the vibration. So a crest got formed completely. So at the end of time t is equal to upper half of the vibration means only half time period it takes. So time is equal to t by 2. So initially when its vibration just starts, brown arrow is the brown arrow direction is very important here. Already we have seen this. The particle 1 just starts moving upwards. So at the end of time t is equal to t by 2, the particle has just returned to the point 1 moving in the downward direction. So that is easy to understand. Then what about this brown arrow? This we did not see. Why? The direction of the brown arrow is shown upwards. This simply means that the particle 2, this particle which is denoted as 2, at the end of the right end of the crest, it's really moving upwards. Why it's really moving upwards? It's easy to understand this. Now the particle 1 has, we are giving the particle 1 only upper half of the vibration. So this will continue to all the other particles. Every particle which is actually vibrating. So starting from the first particle, which is actually given on the upper half of the vibration, this particle one, exactly the same upper half of the vibration, it transmits to the next particle. The next particle transmits the same upper half of the vibration to the next particle. This will continue till the other end. So see here, it can be understood like this from this example very simply, from this diagram very easily. Now when the crust is formed here, already we have seen that a little later. So when the crust is formed here, this particle 2 is still at rest, you see. All these particles beyond 2 are still undisturbed. Undisturbed means they are still at their mean positions, their original position, just like the particle 1 at time t equal to 0, it was at its mean position. So the particle 2 is also like that only. It's still not yet started moving. It's still not disturbed. Disturbance, the string got disturbed only in this region from 1 to 2. So particle 2 is still undisturbed. So a little later what happens is, the crust, already we know that a little later the crust will move, advance further, because it's traveling with velocity. It comes like this, somewhat like this. So somewhat like this it will be coming. So I'll try to use a different color. So color means it takes some more time. So roughly I'll draw the diagram. So the crust will become somewhat like this way. It comes to this position. So what is really happening is, this particle 2 at time t is equal to t by 2, really it is still at rest only. It's but why is the brown arrow shown like this? The reason is it just starts moving like this. How to understand this? It's simple. Now just see here, when the crust has reached here, what is the meaning of crust has reached here? Just see this diagram. Already we have seen this earlier. The shape of the string has become like this, convex shape. It's curved upwards, convex shape. That's really, so that is the meaning of crust has reached here. What is the meaning of crust got formed here earlier? Just don't consider this dashed line here, this dashed line which I have drawn now. So originally at time t is equal to t by 2, so the crust which got formed, the shape of the string itself will be forming this convex shape. Convex means curved upwards, like convex lens. You have learnt a convex lens. This will be a convex lens, magnifying glass. Like this it looks like convex lens. A concave lens looks like this. Many of you might have seen magnifying glass looks like it will be thick in the middle. Now opposite of this lens, some spectacles you have seen, it will be thin in the middle. So that's called concave lens. So don't consider this now, only just as an example I am giving. So this is the shape of the string. So now the crust is advancing forward, that means it's coming like this. Then what is this particle at the center of the crust? Earlier every particle here, earlier at, for example, at this time when the crust has not yet reached here, the string was undisturbed. So this particle at the center of the crust means between the particle 3 and 4, midpoint between the particle 3 and 4, it was like this. It was at its mean position. Mean position means what? Position of rest. So when the crust has reached here, like here at this time, any time greater than t by 2, for example this time is some time, say some time, so 10 seconds or 20 seconds later, when the crust has reached here, where is the particle which is at the center of between 3 and 4, midpoint between 3 and 4, that particle, it has reached here, because the shape of the string has come like this. That means from the mean position earlier, from its position of rest, it has reached the extreme position. That is what is happening here. That means it has completed the upper motion in this upper half of the vibration, to and fro, upper half of the vibration, O to Y, between O and Y we have already called it as upper half of the vibration. So when the particle is going to the top extreme position, it has reached the topmost position, the same position it has reached, the particle which is midpoint between 3 and 4 exactly has reached the topmost position. So always the center of the crust denotes the topmost position. So a little later this crust also will be going away from here. For example, here the crust has reached. This particle will be just as usual returning back to its original, just as this region between 1 and 3 has returned to its original condition. When the crust has passed away from this region, this particle is remaining, has reached the original condition. So that is what is happening when the disturbance is propagating further. So what is happening is, wherever region, to whatever region the crust goes, the particles will be actually disturbed from their main positions to form the convex shape of the string. That is what we have seen. So that is what is happening here. So earlier when the crust got formed here, the disturbance has reached up to the particle 2, it's just still at rest. So when the crust advances a little further, for example the center of the crust has reached from here to here, then where is this particle to? It has gone up. That means as the crust is moving from here to here, as the particle 2 just moves upwards to reach its own extreme position. And when the crust passes away from this region, for example here, this particle to again returns back to the original condition. That is what is happening at a time much greater than t by 2. So what is happening? Every particle, so not just one particle, a particle which is named as 1, even the particle which is named as 2 also, it's going upwards from its own mean position O, its initial position you call it as O again, top extreme position you again call it as Y. Always vibratory motion is denoted by the same symbol, same path. Y O Y dash represents the vibratory motion, any vibratory motion. There are so many practical examples of vibratory motion or oscillatory motion. They are so important. Given a special name also, this particular vibratory motion. So a very simple name it's given. Later in other lessons or in still other classes, higher classes, it will be coming more clearly. So it's practically very important. And this particular example, which we are seeing here, to understand the definition of wave, this is really nothing but called as formation of wave. How a wave is getting formed due to vibrations of particles. This is very important for the understanding of the various properties of waves or various things related to waves. So every particle, not just particle 1, just the same way the particle 2 also is completing its upper half of the vibration. From its own mean position, it's going to its own extreme position and back to the its own mean position. That means exactly upper half of the vibration it's completing. The same thing will be happening to each and every particle where the crust is actually passing through. So every particle will be made to complete its upper half of the vibration. So because of this, so every particle just vibrating, moving it from its own initial position of rest, which is the top extreme position, and again coming back to its own original position. That is mean position. It's called as, always mean position is denoted as what? O. Top extreme position Y. So when it goes even to the bottom extreme position, Y dash. So that is what is happening. So every particle is actually contributing to the propagation of the wave. No, any particle stops from vibrating, we already know that wave stops there and it can't propagate further. Actually, it gets reflected. So why it gets reflected, all such things, properties of waves will be coming a little later. But everything related to wave motion, the most important thing, most powerful thing in science and technology is always the definition. So each and everything what we are seeing in these diagrams will be actually present in the definition. Definition will be just only 3 lines or 4 lines, but each and every detail what we are seeing will be actually present. It will be clearly visible in the 3 line or 4 line definition. So powerful are scientific definitions. If you by heart the definition, it simply means that with simple understanding, each and every word in the definition will be simple to understand by observing the real life example. All the things related to wave motion will be actually present inside the definition itself. When we revise the definition once, it simply means that all the properties of wave motion also will be automatically getting revised. That's the power of a scientific definition. Simplest words, but everything related to that phenomenon in the entire universe will be present in that simple definition. Always it is very useful to by heart the definitions. That is sufficient to understand any situation, however complicated it is. It can be understood easily just with the help of a very simple definition. So just every particle is only vibrating about its own mean position. It's not going. The particle 1 is never going to the particle 5. Only the disturbance is going. But how? Due to the transmission of vibrations from one particle to the other particle. They are only vibrating about their own original positions. Every particle is not leaving its position. It's just vibrating about its own position, not even in the direction of the wave motion. Wave motion is actually rightwards. Disturbance is moving rightwards. The particles are actually moving up and down. Just see here. Because of these vibrations of the particles about their own positions called as mean positions, the wave is propagating. That is the most important, most powerful property of wave motion. What is wave motion or a wave? It's nothing but the disturbance which is actually created, produced at a point where the disturbance is actually really produced starting from the first particle. The disturbance which is actually created at a particular point in the medium. Medium means the string along which the wave is propagating. This disturbance which is created at this point, which is actually traveling, which is propagating due to the vibrations, due to the special property of vibrations of particles only about their mean positions. The particles are never getting, they are never moving along with the wave. They are just vibrating about their own positions, but still making the wave propagate. So this special motion happens only in case of waves. It happens only in case of waves. Whenever any disturbance is moving, for example, you are giving some velocity to a stone, you are throwing a stone. So that velocity of the stone actually is carried by the, so the velocity means it has kinetic energy. That kinetic energy is really carried by the stone wherever it goes. But here the particles are not carrying the disturbance. The particles are only vibrating about their own mean position. They're just at their own position, but still the disturbance is automatically getting transmitted through them. That such a special motion itself is called as wave motion, or simply wave. So that's how the main part of the definition we are able to get. Now just see here, I'm removing this new position, dotted crest, new position of the crest. From here it's moving to here, this dashed line I'm using. So all that I'm removing because original diagram is very important. So see here, I am removing them here. Just observe the cursor compulsorily. I have removed it. Now we got the original diagram. Now just check carefully the exact definition of the wave motion and wave. So the disturbance which is actually getting created at the particle 1, which is in the form of a crest. It's actually moving along the medium, that is through the medium. Medium here is the string. So this disturbance which is actually getting created at the particle 1, at this particular point, which is the location of the particle 1. This disturbance, which in the form of a crest, is moving through the medium due to the vibrations of particles about their mean positions. Now, this kind of special motion of the disturbance itself is called as wave motion. So that's the exact definition of wave motion. Very, very simple definition of wave motion. And what is the meaning of wave? That also we have seen roughly here itself. And what is the wave here? Wave here is nothing but the disturbance itself, which is moving in this special way due to the vibrations of particles. So this disturbance, which is in the form of a crust here, which is moving due to such vibrations, this disturbance which is moving itself is called as a wave. This meaning of wave already we knew from the simple examples which you have seen. Waves formed on the surface of water. How do they look like? They look like such crests or such troughs which actually move along the surface of water. So that's how they move. So still, though we have seen waves on the surface of water, the meaning was actually not, the exact meaning was not so clear. Now the meaning is very clear. What is a wave here? The disturbance which is created at a point in a medium which travels along the medium, or which travels through the medium. Medium here is a string due to the vibrations of particles. So this disturbance which is moving itself is called as a wave. And the motion of, and the special motion of the disturbance which is possible due to the vibrations of particles, the special motion of the disturbance is called as wave motion. So this is the very simple definition of wave and wave motion. But so definitely this is definition of wave and wave motion is very simple, but in a more slightly different way also many textbooks give the definition of wave and wave motion. Now that's actually based on the concept of energy. Now what is energy? So previously we have, so I'll not write anything here. So what is, so just for the sake of convenience, so though I'm writing here, I'll just remove everything again. So what is energy? Energy is the capacity to do work. So this is a simple definition of energy. What is capacity to do work? When is work said to be done? So any object is taken, you are applying a force F on the object, and the object is made to move through some displacement S in the direction of force. Then work done is defined as force into displacement. This is what you have learned in the definition of work. So work is done only when a force acts on a body and a displacement S is moved. The body is moved through a displacement S in the direction of force. Then the product of force and displacement itself is called as work done. So compulsorily for work to be done, force should be producing a displacement S in the direction of the force itself. Then work is said to be done. So who is doing this work? We are applying a force. A human being is applying force means here human being is himself is doing work. So human being has the capacity to do work, or human being has energy. Even the wave also can has the capacity to do work. How do we say that wave has the capacity to do work? Now wherever the wave is going, in that wave you see the particles are vibrating. Particle is vibrating. Moving means what? It has kinetic energy. Because of this kinetic energy of the vibrating particles, the wave also can do work. So how to prove it? Very simple. A moving particle, a moving object, how can it do work? A moving object, when it goes and collides with another object, it applies a force. For example, a moving object here comes this way and hits this object. So it applies a force on this object and pushes it through a displacement. Yes. So it definitely moving object is doing work. Like that, these vibrating particles in the wave also, wherever the wave is present, there the particles are vibrating, you see. So here there is no wave, no vibrations here, that way. So wherever the wave is going, because of the vibrations of the particles here, Definitely, the wave, these vibrating particles have the capacity to do work. That means where are the vibrating particles present? In the wave itself. They belong to the wave itself. So the wave has the capacity to do work. So capacity to do work is nothing but energy. That's why wave is called as energy. So energy, we have seen that it exists in different forms: kinetic energy, potential energy. Like there are different forms of energy, heat energy, like that. There are different forms. So wave is another new form of energy. This is a very important point related to wave or wave motion. So wave is nothing but what? It's a form of energy. But in what is the importance of this form? It is the importance of this form of energy is what? It is in the form of a disturbance which is created at a point in a medium which travels along the medium due to the vibrations of particles of the medium about their mean positions. Such a disturbance itself is called as wave, and this wave itself is nothing but, as we can see, it has a capacity to work, so it's nothing but energy. So another way of defining the wave and wave motion is a wave. Already we have seen the simplest meaning of wave. A wave is nothing but a disturbance which is created at a point in a medium which travels along the medium due to the vibrations of the particles about their mean positions is understood. So such a motion of a disturbance is called as wave motion, and this disturbance which is really moving, for example here crest or here trough, this disturbance which is moving due to the vibrations of particles itself is called as wave. And now because wave is a form of energy, so another way of defining the wave is a wave is energy in the form of a disturbance created at a point in a medium which travels due to the vibrations of particles. That's how another way, a more complete way of defining wave is actually followed by many textbooks. So but now it is better to follow simplest. Energy is a little complicated concept because we have seen how many things are required to understand energy. First, work is required. Work is based on force and displacement, and then from this work done, energy is defined. And the wave, we have seen that it's nothing but energy, and that is, but word is also included in the definition. So energy requires a little more effort to understand. Force is very simple to understand. So anything related to force, best way to define that quantity is in terms of force itself. So here, just for convenience, many textbooks actually avoid this word energy. Because energy means it lot some only physics people can understand energy. So others little difficult to understand energy exactly. Even physics people also, many scientists say that the most complicated quantity in physics is energy itself. It is said to be completely abstract, something imaginary. But how do we, the best way to understand energy is what? In terms of work done. How to understand work done? In terms of force. So it is not very difficult to understand energy also. At least to some extent we can understand energy. So that's why energy being an abstract or imaginary quantity, so many textbooks don't follow this definition of wave in terms of energy. So, but we know the definition of wave now very clearly. It's nothing but a disturbance which created at a point which moves through the medium due to vibrations of particles. And thus, this special motion of the disturbance due to vibrations of particles is called wave motion. And this disturbance which is moving due to vibrations itself is called as wave. So, more accurate way of stating this is, what is wave? It's energy in the form of a disturbance which, when created at a point in a medium, travels through the medium due to vibrations of the particles. So that's all these things are related to the definition of wave and wave motion. Just see here. Now all this is okay. So this is how a crust is moving. Now what about trough? Already you have seen trough also moves the same way with the same velocity, because velocity depends upon the properties of the string. With what material the string is made up of, how tight the string is, whether it's more tight or less tight, how heavy the string is, what material the string is made up of, all such properties velocity will be depending upon. So even a trough that is formed also, in the same string it travels with the same velocity. That's a very important property of any wave. For example, you have learned already, sound travels with some velocity. Sound is a wave. Always it travels with the same velocity, whether it's a loud sound or a less weak sound, always it travels with the same velocity. Always will be behaving like that. Light also travels with some velocity, you have learnt. Always it travels with the same velocity in a particular single medium. For example, in air, light always travels with the same velocity, like that. Light, because light is a wave, the same property holds with all the waves. So whatever things we are seeing here are simple. So nowhere any complication is there. So now just here, now this is what is happening. Now I'm just separating this. This is very important diagram to understand how wave is really propagating. So definitely this is, but to understand the other properties of the waves, let the jerking be continued. So we have jerked this string, left end of the string, only upper half of the vibration we complete. We just jerked it upwards. Upwards means suddenly it's moved up, like this. Just see here. Suddenly the left end of the string is moved up, and then and brought back again to the same position like this. We just moved it upwards like this, the left end of the string, and again moved back here. This is called as upper jerk is given. Now what about if the lower jerk is given? Already we have seen that also. Lower jerk is given, downwards it's moved. This ends, left end of the string is moved downwards means a downward disturbance, that is a trough gets formed. Now let that jerking be continued. Upper jerk we complete. Up jerk means not just in one direction, up and down suddenly, back to the same point. Now after time t is equal to t by 2, that is upper half of the vibration is completed, let the lower half of the vibration be also completed. So that means the string now is jerked downwards. Suddenly down it's moved and again back again. So this is not, now this we are not continuing. What is this diagram? Only upper jerk is given. After that no jerking is done. Then only upper disturbance, that is upward crest only, which already got formed, it travels further. This is okay. This is very good to understand wave motion. Now what about the lower jerk done immediately after the time t by 2? So next lower half of the vibration is also complete. That means the left end of the string, that is the particle 1, which we are holding it in the hand, let it be moved from O to Y dash and then Y dash to O. So then what happens is a trough gets formed. A trough, easy. So observe the cursor compulsorily. A trough gets formed. So this way it looks like. Then how will be the diagram? The diagram will be exactly like this. This is very, 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 very important. It looks exactly like this. This is the diagram. Just see here. This will be the diagram. Just see here. Now upper half of the vibration already completed. So just see here. We move this left end of the string, particle 1, upwards and then downwards. We got the upper disturbance, a convex disturbance crest we got. Now let the disturbance, let the jerking be continued. Now downwards. O to Y dash and Y dash to O. Then what happens? A trough will get formed. This way, trough will be getting formed. But already crest got formed. Will the crest be remaining there at the same point in the next half time period? Next half of the vibration means another t by 2. So what will be the time now? T by 2 plus t by 2. It's what? T by 2 plus t by 2 is what? T it will be. You can just add this and see. T by 2 is half time period plus t by 2. It will be full time period. Time taken will be t. So then a trough will be getting formed. So this will be a trough will be getting formed. So time period is very, very important. Symbol is t. So trough also same symbol is used. So to avoid confusion, I'll just call the trough as t dash. So trough, I'll call it as t dash so that confusion will be avoided. So trough will be getting formed, but by that time already trough which got formed, this trough was present only in the upper half of, that is only in the first half of the time period. So in the next half of the time period, this crest will not be remaining there. It will be going whatever distance it traveled from here to here, because it's traveling with a fixed velocity. So next half of the it travels the same distance, so it just comes here. So this is very, very important. Observe here. The crest will now be, after the next half of the vibration, where will the crest? It will be here, like this. The same crest has moved here, but it has come between the two particles 2 and 3. You see, same distance it travels, and now here in its original position, when the crest was here, now the crest is no more here. It has moved here. The next half of the vibration, but now in the after the end of the next half of the vibration, a trough gets formed. This is how exactly the diagram will be looking like. So that's how one crest and one trough got formed. One complete crest and one complete trough got formed in one time period. That is when the particle 1 has completed both the upper half of the vibration and lower half of the vibration. O to Y it has moved earlier, and back to O it has moved earlier in the first half of the time period, and in the next half of the time period, that is in the downward half of the vibration. So upper half, and this is the downward half of the vibration. O to Y dash and Y dash to O. That is when the downward jerk is completed, a trough gets formed. This is how the diagram will be looking like. This is how really in most of the, that is diagrams, etc., waves are actually shown. One crest is shown, one trough is shown. Such a crest and trough together is called as one complete wave, and the distance itself is called as wavelength. It is called as wavelength. Lambda denotes wavelength. That's how wavelength is actually defined. Wavelength is a very, very important quantity related only to waves. Nothing else will have this quantity wavelength except for waves. So now we are getting a new quantity here. Apart from time period, vibration, now we have another new quantity. a wavelength of a wave. So one crest and one trough together will make up a one complete wave, and that space, that length of that one complete wave itself called as wavelength. So that's what we are getting. Now the most important things related to waves are now, just now we have completed. Now, but one very important thing is already we have seen. Now this why the particle 2 is actually going upwards, why the brown arrow is directed upwards means brown arrows here, or the arrows which are perpendicular to the length of the string actually denote the direction of vibration. So already we understood when the, because the crest is moving rightwards, a little later the crest, the center of the crest will be coming here. So this particle 2 has to come here. That means at this time t is equal to t by 2 half time period, the particle 2, though it's at its position of rest, a little later as the wave comes here, it has to go to this topmost position. That means it should be moving from mean position to the top motion. That's why the direction is shown upwards, because at this instant it's just about to move upwards. So that gives the reason why the particle 2 direction of vibration is shown upwards. So like that, you see here this diagram, the particle 3, why its direction of vibration is shown upwards. The reason is little later the crest will be coming here. That means this particle, the shape of the string comes like this. That means this particle should be going to the topmost position. So from its main position, earlier position of rest was here. When this particle 3 is not yet disturbed, it means the wave has just reached the particle 3, it's not yet disturbed. A little later, when as the wave passes through this particle 3, that means for example the center of the crest comes here, a little later the particle 3 comes to the topmost position. So that means at this instant the particle just started moving upwards. That's why the arrow is showing upwards. And what about this particle 2 direction of arrow? This downward direction we never saw. Except for the particle 1, it's easy to understand. Just see here, particle 1 downward arrow. It's easy to understand because upper half of the vibration is completed. The particle 1 has moved earlier from O to Y and Y to O back again at time t is equal to t by 2. So at time t is equal to t by 2, where is the particle? It has returned back to the mean position O after completing the upper half of the vibration. So it's moving downwards. That's okay. That's simple. Now what about this lower downward direction of particle 2? This is also not difficult to understand. Just observe here. The trough is here, you see. These are very minute things, but very important. All these are very important things related to wave motion. Everything, any doubt in wave motion, we have to come back to this diagram. Whether you are studying the 9th class or 10th class, or when you go to engineering, or when you are doing PhD, or when you become a scientist, or when you are doing a job related to science and technology. Everywhere, any doubt related to the wave motion, we have to come back to this diagram. Such is the importance of this diagram, which actually shows the all the details of wave formation. Any doubt comes, what will help us? This simple diagram will be. There is nothing in the diagram, you see, just some lines, which is really representing the real life situation. But each and every doubt, each and every question related to wave motion, this only can give the complete answer. You can see in the next topic, you can see the importance of this diagram also, other important. So many things are defined from this. Already we got one definition of wavelength, meaning of wavelength we got. And from this exact meaning of wavelength, if we try to pick up, we'll get the complete full scientific definition of wavelength also we'll be getting from this diagram itself. That's the power of this very simple real life example, very simple diagram. So it should never be taken lightly, this diagram. Any doubt comes in the mind related to wave motion, we have to come back here. This topic is simply called as the explanation of the wave. So definition of the wave, or just now we have seen the rough definition of the wave. A wave is a disturbance which propagates, which is created at a point in a medium and which propagates along the medium, that means along the string, due to the vibrations of particles of the medium about their own mean positions. Such a disturbance which is moving due to such vibrations is simply called as wave, and this motion of the wave is called as wave motion. That's the definition, very simple definition. And all these diagrams come under what is called as explanation of the wave motion. So from this we'll get all the properties of wave motion. Many equations can be derived from this diagram. Many very powerful derivations also will be based on this simple diagram. That's the power of this real life example, which actually from which we can understand the formation of the wave motion. Okay, just see this again. So that's how at the end of one time period, one complete wave got formed here, and this wave, which consists of one crest and trough, as usual it moves with a definite velocity. Now coming back to the particle 2, Why the particle 2 its direction is shown downwards? The reason is a little later what happens, the trough will be coming here. And how will be the diagram? So this also I need not show, but I'll just show for the sake of understanding. The trough earlier it was at between particle 1 and this particle. This, what is this particle at the left hand? Particle 1, which is actually shown here. Just always you see the left hand particle is shown as 1. So the particle 1 and 2, the trough is actually present at this time t is equal to t. A little later what happens, time greater than capital T, the trough will be advancing a little forward. So then what is happening to the shape of the string? The center of the trough was here earlier. Now it comes to the exact the particle 2. That means shape of the string has become like this. That means the particle 2 has come down completely to the center of the trough. That means the particle 2 has moved from its own position of rest at time t is equal to t to its downward position, the bottommost point. Center of the crest is always the topmost point, and center of the trough will be always the bottommost point. Just see here, which is the bottommost point in the entire wave. Center of the trough only is the bottommost point. All the other particles are a little higher. So when the center of the trough reaches here, the particle 2 here, the particle 2 really is at the bottommost point. Just observe this. That means it has moved from the mean position to the extreme position. So at time t is equal to t, the particle is at the mean position. A little later, it only moves downwards till the center of the trough reaches here, where it reaches the particle 2 reaches the extreme position. That means really this direction of arrow, which is the brown arrow, is really correct arrow. So now I'll remove this extra. So because the diagrams are tiny diagrams, too many things shown in the diagram will be make the diagram congested. That fine, nothing can. I'm just removing, you see, just by using the delete button. So nowhere any complication is there. Whatever things we are seeing here are simple. Nowhere any complication is there. So this is the trough. So I'm just calling it as t dash again. So this is the exact direction, you see. So this is about the formation of one complete wave in a time period. Now what about if another time period is allowed? So further jerking is continued. For example, now we have completed the particle 1 has one time period, means one vibration is completed. But how we did how we have completed this one vibration? First we have moved the particle 1, the left end of the string, upward and downward. That means upper half of the vibration is completed. That means upward jerk we have given, then a downward jerk is completed. That means lower half of the vibration is also completed. That way one full vibration is completed. So this is all, this way also vibration can be completed. So already we have seen how a vibration is completed. So the best way of completing a vibration is bottommost point to the topmost point, complete upward direction, and then topmost point to the bottommost point, complete downward direction. That is towards the topmost point and then away from the topmost point, complete downwards. Firstly complete upwards, complete. That is definitely one vibration. Another way of counting the vibration is starting from the mean position. So moving to the topmost position and coming back to the same position. That means only in the upper half of the length of the path L. So that is also called as upper half of the vibration. So time taken will be half of the time period. So then moving from the middle position, mean position to the bottommost point and again back here. That means motion is completely, the to and fro motion is only in the lower half of the length. So this is called a lower half of the vibration. This is another way of completing a one full vibration. So that is what we have considered in the wave motion. That is very useful. That's is very useful. But important thing is that is also vibratory motion only. But we have considered separately upper half, which is above the mean position, and lower half, which is below the mean position, touch. That way we are imagining the vibratory motion, one full vibration to be completed this way, upper half and lower half separately, one after the other. Then one full wave got formed. That is time taken is what? Time period. Let that be further continued once again. That means once more upper half of the vibration O to Y and back to Y to O. That is upper jerk is given, upward jerk is completed, and next downward jerk is also completed once again. Then what happens is once more a wave gets formed. But already whatever wave that already got formed at t, now what will be the time then? Once more the upper jerk is completed, lower jerk is also completed. What will be the total time taken? T plus t, it will be 2t. Then how will be the diagram? The diagram, once more this identical wave gets formed. But what about this first wave which got formed at the end of time period t? This first wave will not be present here. It will be shifting to the next. Now at the end of time period t, one vibration, the wave is actually present between the particle 1 and 3. So in the next time period, again it will, so how much distance the disturbance got traveled, the disturbance has moved, the string got, how much distance, how much part of the string got disturbed, this length lambda part of the string got disturbed, means the disturbance traveled at distance of lambda. It is, the disturbance is said to have traveled disturbance lambda, because the string got disturbed only up to this particular distance. So disturbance is said to have traveled, or wave is said to have traveled a distance equal to lambda in one time period. So next time period the same thing will happen. Again the same, this particular wave travels the same distance. It will just exactly come here between this. Like this it will become. So I'm just showing it roughly. Observe. But I don't want to change this diagram. Immediately I'll remove this, erase it. So just for the sake of understanding I'm showing. So this first wave which already got formed in the next time interval t. This first wave actually moves here. But in the next time interval, what is happening? Same vibratory motion, upper jerk is completed, lower jerk, so a second wave gets formed here, which looks exactly like this as when the first wave was present here. Then how will be the diagram? It looks like this. See here, this is how it looks like. This way, as the jerking of the left hand is continued again and again, upper jerk, downward, lower jerk, upper jerk, lower jerk is continuously continued. This way vibratory motion is continuously done again and again. The left end of the string is continuously vibrated. More and more waves will be getting formed, but all of them, the important thing is all of them will be moving steadily with a velocity v. So till the waves continuously reach the other end of the string. That's how wave motion can be continuously produced. Now I'll just remove this, and I'll remove this part also. So this extra I have drawn here, I'm just removing this by pressing the deleting button. See here, I'm deleting, just observe the cursor. The diagram again becomes original, because original diagram is very important, because this is the diagram which we have to trust when any question arises in our mind, or in the textbooks we are seeing any question. However complicated it is, very easily it can be solved. The answer can be found out with the help of this very simple diagram. Whether you are in the ninth class, or whether you are doing, you are trying to find out a new thing when you become a scientist. Any situation, this is the diagram which always we can trust. That's the power of this very simple line diagrams. Very simple line diagram. So such line diagrams, that's why they are called as scientific diagrams, because everything related to that particular phenomenon observed by a scientist actually will be hidden, will be actually holding in this diagram. So that's the use of this particular diagram. It can answer any question related to wave motion. So now we got many things related to wave motion here. From this, again, very important thing is various quantities related to wave motion. So see here, already we got one quantity, wavelength. Here, more accurately, just by observing another one or two small things from the same diagram, one or two more points, one or two more words, very accurate words can be found to be related to the wavelength. From that we'll get the exact scientific definition of wavelength also. Not just the scientific definition of wavelength. Already we have seen the definition of time period also. Very simple definition, time taken to complete one vibration. And from this wave motion we'll get another equally powerful definition of time period again, related to the wave motion also we'll be getting. So just we have just seen the time period definition related to the vibration. Even in terms of wave motion also we can get the definition of time period. That also will come from the same diagram. Very simple, this particular diagram. T is equal to T at this instant, T time is equal to time period. So that's the power of these very simple diagrams. So nowhere any complication is there. Whatever things we are seeing here are very simple. Nowhere any complication is there. Now just observe the importance of this particular diagram. Already I said it's very important. Now how much time we have taken to understand up to here the formation of wave? Just see here, almost about 1 hour or a little more than 1 hour. But how many marks formation of wave consists? It's actually carries explanation. So this explanation is nothing but really formation of wave itself. Already I said many times that I'll be giving this entire notes. Actually, it's the running notes actually. very neatly I'll give the entire notes in order. So without for example, the rough column, for example, this is the rough column. Rough columns also, I'll just put them exactly in order in the rough column, right side of the page. I'll put everything so that nothing will be actually missing in the actual notes. So the actual syllabus topic, I'll give very neatly in the fair column. That way I'll just so no single point I'll be missing in the running notes also. It's not exactly running note. Running notes means it's written roughly during the class itself, but I'll give the notes very clearly. Directly I'll display it after I'm the notes is after I make the notes ready very clearly. So not even a single point which is completed during the explanation will be missing in the running notes. The actual topic, including the explanation. For example, the crust is traveling a distance, some distance in a time t greater than t by 2. All that everything I'll be writing, displaying clearly. So at the end of the class, last, for example, the class is say 100 minutes. Last 2 or 3 minutes, I'll just display all the 3 pages or 4 pages, whatever number of pages it takes, everything clearly in order I'll be putting. You can just directly, I'll just provide the link also. YouTube link also I'll just be providing, download link also at the title of the video in the YouTube. So directly you can download it, or you can download it and take the printout, or you can just download it and copy down the notes in the classwork book or notebook, classwork notebook. You can just copy down whatever is convenient. The best thing is to avoid the wastage of time, because I am preparing it in a regular orderly manner. It takes considerable time. Directly you can take the printout and learn from that. How to learn it? For example, here carrying 2 marks, only definition. That means explanation will be taking about 7 to 8 lines, including the diagram. It will not be required. Like that, everything I will be providing clearly how to study also. The best thing is to take the printout, because I am making the notes ready, so that your time will not be getting, actually you're be having more time available for solving problems, or for reading other topics related to this particular lesson from other books, either other textbooks from different parts of the world, or solving different problems from different textbooks. More times can be spent on that. So now coming back here, so it took about almost 1 hour. Now how many marks it's carrying? The explanation, which is really what? The formation of the wave. So which is really the explanation of the side heading, which we already seen. The side heading is what? Wave or wave motion. Already we have, I've displayed the side heading also, wave and wave motion. That's the side heading definition we have seen. Next, under explanation, this will be actually coming. So this explanation itself is also called as formation of the wave. So it took almost more than 1 hour for completing this. So we have seen many detailed points also we have seen. All these things will not be getting wasted. So it will not be really unimportant. So it's really most important thing related to waves and wave motion. Now, immediate next topic, you see, it carries about 2 to 4 marks, or even 2 to 5 marks. So many small topics are there in this particular topic. It's a big topic called as quantities related to wave motion. So all these small topics which form the complete big topic carrying almost 5 marks, quantities related to wave motion, everything directly from this single diagram in just one fraction of a second it can be obtained. That's the power of this diagram. And next you have another two small derivations. One is a 3 marks derivation, one is a 4 marks derivation. 4 marks means almost it's close to an essay question. Essay question, many boards carry about a 5 marks. Some boards carry even 8 marks, but in the 8 marks, actual theory will be consisting of only 5 marks, and 3 marks will be a problem. So even essay question, roughly strictly speaking, single topic of the essay question carries 5 marks. So next topic is a 4 marks topic. Even that also, in just one step it can be obtained from the diagram. So this time which you are spending on understanding each and every detail of the formation of the wave will never get wasted, because The other big topics, fraction of a second, they'll be completed within no time. So this carrying about maybe 1 mark in some objective question, but in the essay question, the time will be actually compensated. So it took 1 hour essay question, so it's carrying only 1 mark, you see, from practical point of view, reality point of view, it's carrying only 1 mark in the exam, but the 4 mark answer is entirely based on this. Within 1 minute, it will be completed. So there you are actually making up the time. So don't think that you're spending too much time in understanding the formation of the wave. It's really useful. That this only is useful. All the other things are wasted in the lesson without understanding the formation of wave. Don't think that time is getting wasted. This only will be really practically useful, not just in the ninth class. Even when you become a scientist or an engineer trying to solve some really practical problem, also this will be really helpful because waves have wide applications in daily life. So now going to the topic directly. So already I said the topic is quantities related to wave motion. Now this can carry up to 4 to 5 marks. You see here. So very important. Carrying about 4 marks, and each quantity here is actually carries about 2 marks. Many quantities are there related to wave motion. Now, what are these quantities? Already I said the first quantity is the which we already completed, time period. Why we are doing this time period again? So already we have seen the definition of time period. So that definition is related to vibratory motion, but without vibratory motion, wave motion will not be possible. So the same time period can be defined using wave motion also with the help of these simple diagrams related to the formation of the wave. Now just observe here the time taken. So first definition already we have seen. What is time period? It is the time taken for, just see here, time taken for one vibration. That's what we have seen the definition of vibratory motion. That is in the definition of one vibration or one oscillation. That time taken for one vibration or one oscillation itself is called as time period. And what is the second definition? Why second definition is given? The second definition is given because vibratory motion produces wave motion, as we have seen in the example. Just see here, in a time equal to time period, just observe here, I'm not going back to the earlier things again. Original time t is equal to 0, the vibration starts for the particle 1. So after time is equal to t by 2, half time period, one crest got formed. In the next time, t is equal to t by 2. That means total time taken is how much? Already we have seen t by 2 plus t by 2. That is one time period. Along with the crest, a trough also gets formed. And how will be the diagram? Already we have seen. Like this it will be looking like. This is what it looks like. So after one full time period, when the particle 1 has completed one full vibration, that is upper half of the vibration is completed first half time period t by 2, next half time period t by 2, the lower half of the vibration is also completed for the particle 1. Then we have seen that one full wave gets formed. This is very vital, very important, the most important thing related to the wave motion. So nobody should be missing this. If you are missing this, the entire lesson will be disappearing. There's no use in learning the entire lesson without the understanding of this. There's nothing in this. It takes some time, considerable time has to be spent, maybe 30 minutes or so. But compulsorily spend this time and just listen to this. If you already missed this, directly you're trying to come to the definition of the time period. So again, go back and listen to this if you did not listen. Once you have listened, that is sufficient. Directly you go to the printouts. Directly you go to the last 2 minutes of this particular video and get the printouts, download the links of the printout, just revise the printouts, that is sufficient. Each and every line in the printout will be actually explaining all the details, but in less time. So video only is taking more time. So actual notes will be very simple. You need not listen to the video again and again. Once you have listened to the particular class, immediately you have to come get the printouts and check any point you want to add. You can add into that in the printout itself. Supposing you like some point during the understanding of the wave motion, you liked some point, and in the actual printout it's missing. that is link of the which I said I'm sending about 3 to 4 pages. The running notes will be that link, that particular point is missing. Then you add that point if you feel that point is very important for the sake of understanding. That way you have to be preparing your printer, your running notes on your own. So most of it, 99% I am providing it. Remaining 1%, if you feel any point is missing, you add here that point, so that always it will be, you will be able to remember that. So definitions are the most powerful things. Many times I said that in science and technology, definitions are the most powerful things. You have to by heart the definition. There is no other way. Every lesson will have only 3 or 4 definitions. They have to be by hearted. You can't escape from the definitions. If we have the definitions in the mind, word to word, everything in the universe can be understood just with the help of the such simple definitions. Definitions always are simple because they were given by scientists to help us in understanding of the universe. Now just see here, in one time period, just see here, where is up to what distance the wave has advanced from particle 1 to particle 3. It has advanced, the wave has advanced from particle 1 to particle 3. So now just observe here, in one time period, earlier at time t is equal to 0, just see here, earlier at time t is equal to 0, there was no wave present here. The entire string was undisturbed. But once one time period is complete, just see here, be very careful. We are not doing anything new, just formation of the wave. That only we are just revising again. After one time period is completed, one full wave has got formed. One full wave. And how is this wave passing? It's actually passing from left side to right side. Through different points it's passing. So next, again observe here, in the next time period, after one time period, next another time period, what is happening? One more wave got formed here, and earlier wave which already was formed at time is equal to time period, one full wave which has got formed, through the particle 3 it has passed and reached the particle 5. That's what is shown in the diagram. Already you have seen this. Just observe here, in one time period, through the particle 3, observe here, in one time, that is second time period, just observe here, from t to t plus t, that is in the second time period, one full wave, crest and trough, already you have seen that it forms one full wave. One full wave has passed through the point 3, through this point where the particle 3 is present. So time period, now we have another new meaning. This is the time taken by one complete wave to pass through a point like particle 3, not just particle 3, in the first time period through particle O, that is through the particle 1, to the point representing the particle 1, again one full wave has passed through this point. It got formed means something like it, because it's passing from left to right, we can say that the disturbance wave has passed from left to right, started from particle 1 only and ended up here, reached here in one time period. So this is even more clearer. In one time period, that is in the second time period, one full wave has passed through this. Again the next time period, even through the particle 5 also, one full wave will be passing in another one time period. That means time t is equal to 3t. Like that, time period is nothing but time taken by one complete wave to pass through any point, or simply time taken by one wave to pass through a point is called as time period. So this is the second definition for time period, in terms of, first is in terms of just plain ordinary vibration, but second is in terms of wave motion. That's why this is also considered to be very, very important. So it is the time taken, I'm writing in short, you see, time period is the time taken by one wave to pass through. I'm writing in short, you see, through, I'm writing in short spelling, THRU. So it should be written in full word. So to save time, I'm not writing, maintaining any capital and small, but in the running notes, I'll make everything fair, exact, no shortcuts. Exactly, I'll be sending the link of the running notes. Time taken by the same thing. I'll just make the words a little more neat. Same order, definition 1, definition 2. I'll write them more neatly. Time taken by one wave to pass through any point. That's all. This is a simple definition. So that's what we are getting, time period. Nowhere any complication is there. Now just observe another one thing. Next is another very, very powerful definition. It's called as frequency, n. So what is frequency n? Now frequency n, now just see here, the particle is actually continuously, when One vibration is completed by the particle one wave has passed through this point. Next, a second vibration is completed, a second wave also has passed through this point. So first one vibration is completed by the particle, one wave got formed. That means it can be imagined that it has passed through the point because it's passing from left to right, the wave. So next two vibrations are completed, two waves have passed. So this total number of vibrations made in 1 second is defined as frequency. So this is simple definition of frequency. So nowhere any complication is there here. Just observe here, we have a new quantity here. So frequency n, frequency means how frequently the particle is vibrating. So more frequently means more number of vibrations are made in 1 second. Less frequently it's vibrating means less number of vibrations are made in 1 second. Due to this reason, frequency tells us how quickly the vibrations are made. How quickly means in 1 second more vibrations are made means very quickly the vibrations are completed. That's why frequency is more means number of vibrations in 1 second is more. 1 second means unit time. Frequency is less, frequency of vibration less means number of vibrations in unit time is less. That's why frequency is defined as number of vibrations in 1 second or number of vibrations. Just observe here the definition. Frequency is the number of vibrations. I'm writing in short, you see, in 1 second. This is defined as frequency. Very simple definition. I'm not writing in full detail, just roughly. The only the meaning must be understood because we have the same. So already the most detailed, minute test points, even how the particle is vibrating, in what is the direction of vibration, every detail we have seen. That is sufficient. Now all the other things will be directly following this very simple wave formation itself. From the simple diagram, each and every detail will be coming, each and every. So frequency is the number of vibrations in 1 second made by vibrating particle or even by vibrating body. We have seen the best example of vibrating body is what? A load suspended at the end of a spring. Already we have seen that example. Load suspended at the end of a spring, when we pull the load down and leave it, it starts vibrating. In that case also, number of vibrations in 1 second is called as frequency of vibrations. Now this is definition 1. Now the same definition, frequency, is given in terms of wave motion also. That's called definition 2. What is the definition 2? Just here, when one vibration is completed, one wave has passed through this point. For example, through this point, one wave has passed. Not only through this point, already we have seen, when one vibration, that means in one time period, one wave has passed. In two vibrations, two waves will be passing. When two vibrations are completed by this particle, two waves have passed through this point. Not only this point, to every point this will be happening. So in 1 second, n vibrations are made. So frequency is n, means it simply means that symbol for frequency is n. Why the symbol is taken as n? Because its frequency is the number of vibrations. So in many textbooks, even in the central syllabus textbook also, you see another symbol is used for frequency. It's called nu. Nu. Even this symbol also is actually throughout the world. This symbol also is followed. N is also followed. So any symbol can be followed, but nu is actually looks like V. That's why many textbooks don't follow frequency. Nu is not actually followed. Many textbooks actually. So any symbol can be used. Some textbooks follow nu, some textbooks follow n. Doesn't matter because it's a number of vibrations. N is used. So number of 10 vibrations are made in 1 second means frequency is said to be 10 vibrations per second. 20 vibrations are made in 1 second means frequency is said to be 20 vibrations per second. It's a number, so symbol n can be used, or like in most of the other textbooks, nu also can be used. It doesn't matter. So there's no difference at all. So next, what is the other definition? So in 1 second, n vibrations are made. One vibration is made means one wave passes through any point. Two vibrations, two waves. N vibrations are made means what is the meaning? N waves are passing through any point. So n vibrations in 1 second means n waves in 1 second. So frequency is n vibrations per second means automatically it means n waves are passing in 1 second. So number, it's the same thing. So frequency can be defined as number of vibrations in 1 second, which is same as number of waves passing in 1 second. So frequency can be defined in both ways. It is the number of vibrations made by vibrating particle in 1 second, or made by vibrating body or oscillating body in 1 second, or it's the number of waves passing through any point in 1 second. So this is the other definition. So I have written everything in short. You see, what is the definition of frequency in terms of waves? Number of waves passing through any point in 1 second. N waves in 1 second. So frequency number of waves will be passing. N is frequency means exactly same number of waves will be passing in 1 second. So what will be the final definition? Number of waves, number of vibrations in 1 second, or number of waves passing through any point in 1 second. So this is the definition of frequency. Now just observe here. Now consider a simple example of frequency. So frequency is, say, 10 vibrations are made in 1 second. What will be the frequency? 10 vibrations per second. 20 vibrations are made in 1 second means 20 vibrations per second, or it can also be called as 20 oscillations per second. Sometimes even cycles also, one vibration is sometimes called as one cycle. So 10 cycles per second. Anyway, it can be called, or in terms of wave motion, it can be called as 10 waves in 1 second. That way frequency. Anyway, it can be called. So 10 vibrations per second, 20 vibrations per second, 30 vibrations. But simplest of all the names for the unit of your frequency, the simplest of all ways of expressing the frequency is vibrations per second. So cycles per second, oscillations per second, waves, anything can be used. Simplest way of expressing frequency is vibration in terms of vibrations per second. So 20 vibrations per second, 30 vibrations per second. So from this easily we can guess that. So length of an object is 10 meters, 20 meters, 30 meters, 40 meters, like that, different objects. Meter is the unit of length, like that. Here, what is the unit of frequency? Vibration per second. So units of frequency is what? Simply, it's very simple. Unit of frequency is what? Vibration per second. So second is usually not written as SCC, it's simply written as S. Only for the sake of understanding, I have written it as SCC. So more accurately means it should be written as S. So vibration per second is the unit of frequency. So a scientist by name Hertz, he invented many things related to vibratory motion and wave motion. So his name is actually selected to represent the unit of frequency, vibration per second. So name of a scientist, which is used to denote, for example, unit of force is what already you have learned. What is the unit of force exactly speaking? Unit of force is given by mass into acceleration. So from this, mass unit is what? Kilogram. Unit of acceleration is what? Meters per second square. So kilogram meters per second is square is the unit of force. So this itself is called as, in shortcut, it's called as Newton, named after scientist Newton, who gave the Newton's second law. This is which is said to be the most powerful law in the universe. Newton's second law is said to be the most powerful law in the universe, even far superior to all the other laws. For example, conservation laws, even Einstein's principle, E is equal to mc square. Newton's law is said to be even more powerful than all the laws in the universe. So unit of force, kilogram meters per second square, is a real unit. So that itself is called as Newton because it's the name of a scientist. Symbol is written in capital letters and full name of the unit is written in small letter. So the same way, unit of frequency, vibration per second, because it's also called as hertz. So vibration per second is also written as what? Hertz. So full name is written with in small letter, small h, and symbol is written hz, capital letter it's written. So that's about the frequency. See here, so already we completed 2 marks plus 2 marks, 4 marks. How much time it took? Very little time, directly from the diagram. Even the other things are even lesser. They take even lesser time. So next, very simple definition. So whatever things we are seeing here are simple. So the next definition is after frequency is the definition of amplitude. So this is another third quantity related to the wave motion. So it is simply called as amplitude of the wave. So its symbol is capital A. So what is amplitude of the wave? So this is also very easily it can be understood from this simple example. So again, it also has two definitions. First is the definition 1 in terms of vibratory motion. Next, the same way the definition 2 in terms of wave motion also it can be given. So firstly, definition in terms of vibratory motion. Now consider the example of the vibratory motion. The best example is not just the vibrating particle, which you have seen which you have considered the first particle 1, which is the left end of this string or rope in which the wave is actually formed. Now considering the original example of vibratory motion or oscillatory motion, a load suspended at the end of a spring. So consider that example. So I'm taking that particular same diagram. So this is the load suspended at the end of a spring. So when the load is actually made to execute vibrations, so we are just pulling the load downwards to the point y dash and then at the bottom extreme position, lower extreme position y dash, and then leaving it. Then it's actually going to the position y and again back to y dash. So that way it's executing vibratory motion. Now consider the any position of the load. So during its oscillatory motion, or vibratory motion, imagine that the load is actually moving from the mean position O upwards this way. So after some time, let it reach a position P. So P is the final position. So then the displacement of the load. So load is now at this particular position, say this way. Then the displacement of the load from the mean position is OP. Displacement is the shortest distance between the initial and final position. Simply, it's nothing but the length of the straight line joining the initial position to the final position. So OP is the displacement. So this displacement is denoted as Y. Displacement from the mean position is denoted as Y. For convenience, it's taken as a small y because we are taking the y-axis. So y over y dash denotes the y-axis. X o x dash is something like so in coordinate geometry you have learnt. So this is an x-axis, ox. This is the y-axis. X-axis is taken horizontally, and y-axis is taken. This direction is called as vertical direction. So we are taking the vibrations along a vertical path. So on the y-axis, this displacement is denoted by small y for convenience. So as the load is actually moving upwards, OP increases. So displacement y is what? OP. So I'll just write this a little more clearly. So the displacement y is what here? Simply OP. So as the load moves away from the mean position O during its upward motion, OP increases continuously. So, and finally, when the load reaches the top extreme position Y, that means the load position P is now coinciding with the top extreme position Y, then the displacement OP is equal to OY, that's maximum. So this maximum displacement, so from O to Y, this is the maximum displacement of the vibrating body or oscillating body, is the maximum displacement from the mean position O. This itself is called as amplitude. So amplitude definition is very simple. It is the maximum displacement of the vibrating body from the mean position. So then what about the wave motion? So in the wave motion also, see here once again. So here we are considering in the wave motion also the same definition can be applied. So what is amplitude now? Maximum displacement. Maximum displacement from mean position. Mean position means what? O. So I'm not writing other details here. So in the diagram itself, it's very clear. The original diagram of the vibratory motion of a load suspended at the end of a spring. Maximum displacement from the mean position. So how to apply that here for the wave? Now just observe here. In the wave, you see here, at time t is equal to 0, the particle 1 started moving from the mean position upwards. Because firstly it's moved given an upward jerk, the particle 1. Because the left end of the string is particle, left end is given upward jerk, that is the upper half of the vibration is completed. As the particle 1 moves, particle 1 can be taken as its position can be taken as P as usual. The path is again the same path y o y dash. So as it is going upwards continuously, its displacement from the mean position O, that means OP is increasing. When it is reaching the extreme position, it has become maximum. So OY here is the amplitude here. So when it's reaching the extreme position, its displacement is maximum, it's nothing but amplitude. Now, so consider the particle 2. This particle 2, earlier it was at rest. So for example here, just observe here. So this time this particle 2 was at rest earlier. So at time t is equal to t by 2 also, the wave has not yet disturbance. Wave is nothing but disturbance here, has not yet reached the, just to reach the particle 2. So it just starts moving upwards. Still it's at mean position, its mean position of rest. Its position of rest, that is mean position O only. Here again we can consider a path y over dash again. It's still at its mean position O. So its displacement is still 0 only. But a little later, what is happening? The center of the crust is reaching here. So when the center of the crust is reaching, among all the different particles in the crust, which is having maximum displacement from the mean position, only the center of the crust, the particle at the center of the crust is having maximum displacement. So which is nothing but amplitude. So what is this amplitude here? It's nothing but the width of the crust or the vertical height of the crust. So even for the vibrating particles in a during wave motion in a medium, that is here what is the medium through which the wave is passing? The string or the rope is the medium through which the wave is passing. All particles have their own amplitude. So from law of conservation of energy, because total energy remains constant, whether it's kinetic energy or any form of energy is remaining constant, all these particles will have, based on the law of conservation of energy, all of them will be having the same kinetic energy. Whenever it's vibrating, with whatever kinetic energy or with whatever energy the first particle has vibrated, the same energy is transmitted to all the particles till the last particle. So every particle will have the same energy. Due to this reason, it can be shown that the amplitude will be same for all the particles. And what is this amplitude of each vibrating particle? Is nothing but the width of the crest, or the vertical width. This direction is usually called as vertical, this is horizontal. The vertical or perpendicular width of the crest itself is nothing but the amplitude of the wave. So, or we can just take even trough also. Just observe here. So trough. So when the trough is here, the center of the trough, you see, it is as maximum distance or maximum displacement from the mean position. So the center of the crust, if trough is taken here, it's at this particular position. So earlier when the wave was not present here, all these particles were here this way. When wave was not present here, actually the string was completely straight from here to here. All the particles are at their mean positions initially, were at their mean positions. Once the trough got formed here, this particle at the center of this trough, earlier when it was at the mean position, the displacement was 0. But now it has reached the extreme position down. So its displacement is maximum. So that is the amplitude here, but in the downward direction. Upward direction amplitude is called as plus amplitude, positive amplitude. Downward direction amplitude is called as negative minus amplitude. It's usually, that's how they are actually represented. Top upward displacement is positive, downward displacement is negative. The displacement is a vector quantity. In one direction it's positive, means in the opposite direction vector quantity is usually taken as a negative. So the same way here, in the trough, the displacement is maximum center of the crest trough, so which is actually a negative amplitude. So which is again nothing but the vertical width of the trough. So maximum displacement from the mean position is the original definition of amplitude in terms of vibrating particles. Or what is the second definition? From the diagram, easily we are getting the second definition. It is what? The vertical, or it's also called as the perpendicular width of the crest or trough. So this is the second definition in terms of the same amplitude in terms of wave motion. So whatever things we are seeing here are simple, nowhere any complication is there. Now the next definition is, so just observe the previous definitions once. So firstly we have seen the definition of time period. So just see here the definition of time period. Next we have seen the definition of frequency, and next we have seen the definition of amplitude. So next very powerful definition, which is actually almost the most important definition among all the quantities, the definition of wavelength. This also roughly we have seen the definition of wavelength also previously. This is considered to be the most powerful quantity among all the waves. Only a wave will have the wavelength. For example, a vibrating particle cannot have a wavelength. A vibrating particle cannot have a wavelength. Only a wave can have a wavelength. So what is this wavelength? Already we have seen in the diagram. So this is really nothing but the distance occupied or the length occupied by one complete wave. But a more clearer definition is there for wavelength. Now just observe here. So earlier the entire string was completely straight. I don't want to take that diagram again. So for example, if you want to see the diagram, it's like this simple diagram. There's nothing here. The diagram complicated. So earlier when the wave was not formed in the string was entirely undisturbed. Entire string was straight. But in a time period, in one time period when the particle 1 is completed, one full wave got formed here. That's what we have seen in this diagram. So the disturbance has traveled. So slowly, step by step, the disturbance has traveled. This is how the disturbance we have seen started from the left side. So the string got disturbed up to here. Still beyond the particle 3, there is no disturbance yet traveled or formed beyond the particle 3. but the disturbance or this disturbance which is traveling due to vibrations itself is called as wave. So the wave has traveled how much distance? Exactly equal to wavelength. But in what time? In time period. So this is the simple definition of wavelength. So wavelength. So only very one main definition, simple definition. It is nothing but what? It is the distance traveled by wave in one time period. So distance traveled by a wave in one time period. Time period means in time t seconds. Time period is t means t seconds. Usually time period is measured in seconds already we have seen. So time period is 10 seconds, 15 seconds like that. In general it's taken as capital T seconds. So in that one time period t seconds, whatever distance the wave travels, the disturbance travels, that itself is defined as wavelength. So just remember this definition is a very very powerful definition. Just from this definition we can get a one very very important derivation which actually carries around 4 marks. That's why I said formation of the wave, though it's carrying 1 mark or sometimes it will never given. So but it's very very important objective questions are based on this 1 mark questions. Though it's carrying only 1 mark, in the exam only one such question can be asked at a time. Though it took a lot of time, big questions, for example 3 marks, 4 marks questions. Even this is what we are doing now, quantities of wave motion. It's also a 4 marks question because 2 to 3 definitions will be asked from this, or at least minimum 2 will be asked from the different quantities. So it's carrying easily 4 marks directly within very much comparative, very less time they can be completed. So that's the thing. So one 4 marks question directly applying this definition, just one step we can get the 4 marks derivation here. That's the power of this very simple definition of wavelength. So the previous definitions, 3 quantities related to wave motion, we have seen that each quantity, for example, time period had 2 definitions. Next, frequency, amplitude, they also had two definitions. Only wavelength here we have one definition. So this is the main definition. So the reason is previously in each definition, each quantity was defined in terms of vibration of the particle and also in terms of the wave motion or in terms of wave also. So wavelength is present only for a wave. So vibrating particles cannot have any wavelength. So due to that reason, only one definition is there. But still, a wave consists of vibrating particles. Without vibrations, wave cannot propagate. Compulsory vibrations are required. Already we have seen for wave to propagate. No vibrations, no wave. So due to this reason, in terms of vibrating particles also, wavelength can be roughly defined. Though a single vibrating particle cannot have any wavelength, but still a large number of vibrating particles are required or large number of vibrations are required for wave to propagate. Due to this reason, even a second definition is also possible. Though I am not writing the second definition here, but once just look at the second definition, directly it can be understood from the diagram itself again. Now here you see, what is this here? This distance already have seen that it's equal to the wavelength. So even from this definition also. But what is this wavelength here? It's the distance between the two ends of the wave. This is called as complete wave. One complete wave. One crest and trough. Already have seen that it's one complete wave. So what is wavelength now? It's the distance between two particles. Where are the two particles? Particle 1 and particle 3. They are situated where? At the two ends of the wave. One complete wave. So this distance between two particles at the two ends of one complete wave can also be defined as wavelength. So this way in terms of particles also wavelength can be defined. And also see here many definitions can be observed here very easily from the diagram here. So here it can also be seen that the length occupied by one complete wave is also called as wavelength. So that's also another simple meaning of wavelength. And next, still more definitions we can get. All the definitions directly follow from this diagram of the wave formation. Such is the importance of wave formation. Many definitions we are getting. Similarly, derivations also we will be getting. And many properties related to waves also can be understood from this simple diagram of the wave formation. So any doubt comes, whether you are studying 9th class or even when you become a scientist also, or even you become an engineer also, any problem related to waves is there in engineering or in science or in some scientific work, immediately we have to just take the help of wave formation. Now this is the best simplest exam diagram which actually explains the wave formation. So this we have to come back here to this diagram to find out the answer. So that's such is the importance of wave formation to study waves. or wave motion. So it's not just useful in study of general waves. It's also very useful to study sound also, because sound also travels in the form of waves. And next, another very important thing is light also. Light also travels in the form of waves. There are many examples, other examples of waves also in nature. Everywhere the same wave formation will be sufficient to solve even the most complicated problem also. So now, what is the other definition? Directly in the diagram we can see here. Now just consider the two crests, the centers of the two crests. You see exactly the centers of the two crests. Already we have seen that in the crest, just see here, in the crest, which is the highest particle, the center of the crest. So every particle, already we have seen in the diagram, just see the diagram, original diagram. Every particle here, not just the first particle, it's actually executing vibratory motion along the path y dash. So for the wave to propagate, each and every particle will undergo the same identical vibratory motion just as the particle 1. So whatever vibration we are giving the particle 1, same vibration is actually transmitted from law of conservation of energy to all the other remaining particles, assuming that there is no loss of energy based on the law of conservation of energy. How law of conservation of energy is used to prove this? All the particles will be having exactly identical vibrations. More clearly, this can be understood from later other topics which come in still other lessons related to physics. Still in higher classes, it will be coming more clearly. Or in certain topics of this year itself also, one or two places this will be coming a little more detail, in a little more detailed manner. So that will be entirely based on what a very powerful law, the law of conservation of energy, which you already learnt in the previous topics or previous years. So now just observe here another very simple definition. Now take the centers of the crust. Now among all the other particles, which is the highest particle in the crust? The center of the crust is, already we have seen that it is the highest particle. It's at the highest position above the mean position. So if we take the center of the crust, this will be, now this particular particle, earlier we have already seen that, for example, this is the center of the crust. So where is the position of the crust here? Crust is between 2 and 3 early. So exactly at the midpoint the center of the crust is present. So earlier when there was no disturbance here, for example here, just observe here, earlier when there was no disturbance here, actually for this we'll consider this particular diagram. The center of the crust earlier was at mean position, position of rest. Once the disturbance or wave got formed, the shape of the string is not just straight now, it has become curved upwards, forming the crest. So where is this particle at the midpoint between particle 1 and particle 2? Earlier it was at mean position, now it is at the extreme position. That's what we have seen. Its center of the crust will be the extreme position during vibration of the particle which is located at the center of the crust. It's at the extreme position. All the other particles will not be at their extreme positions. So only this is at the extreme position. What is this? So only this is at the extreme position. And what is the displacement here from the mean position? It's the maximum. So it's called as, that itself is called as amplitude. Just previously we have seen, previous definition itself. So now considering that here in this particular diagram, so now at a time t is equal to t, we have seen that two waves are formed here. Actually, two waves have been formed here at the end of time t is equal to t. So in these two waves, you take the centers of these two neighboring crests. Now, how are these two particles at these two neighboring crests? They are at the extreme positions. So even here for this particle 1, which is the extreme position y. So such a vibratory motion, such a vibrational path y over y dash will be present for each and every particle, because every particle will be having identical vibratory motion. Due to that only the wave is propagating. All these things previously we have done. So at the centers of the two crests here, where are the particles? Means exactly at their extreme positions in their own similar path y over y dash, path of vibration y over y dash. It's there at the extreme positions. And extreme position means the particle will come to rest at the extreme position. Already we have seen. At the mean position, it can be either going upwards or downwards. But once it reaches the extreme position, it stops there and it turns back in the opposite or downward direction. So here these two particles really they are at the extreme position. They are at position of rest. So this in the next moment they'll be only going downwards. So that is the situation, that is the state of vibration of these two particles at the centers of the two crests. Now such a state of vibration is simply called as phase. It is simply called as phase. This word phase is very important. Just remember this. So I'll not be putting this word, I'll just remove this immediately next. But just remember this word phase. Phase is what? Is a state of vibration. How are the states of vibration here? exactly similar states of vibration. So such two particles are said to be in phase. The same thing will happen even for the next wave also. For example, at time t is equal to 3t, in time two time periods, two waves got formed. In three time periods, if we take, three waves will get formed. So third wave will be looking like this. So roughly the diagram, I'll not draw the diagram neatly because I'll remove this because this is the main diagram for answering this particular question called as formation of a wave. So later I'll remove this. So extra things only for the sake of understanding I'm drawing here. So you should not be drawing this. Just remember this. Even if you want to draw this, you draw it in a rough column. Any extra diagram, you draw it in the rough column, or extra point, you write in the rough column. So that will be the best actually, so that the actual syllabus will not be getting disturbed. So in time, three time periods, three waves will be actually getting formed. Now just you take the next crest also. That is also in the same state of vibration, similar to these two particles at the centers of the two crests. So all these two, three particles are somewhat in the same state of vibration, similar states of vibration. So they are said to be in phase. But these two particles at the centers of the nearest crest will be the particles which are the nearest, which are in phase. And what is the distance between these two particles? Just observe here. Now I'll try to use a different color. Just observe this quickly. It's very simple. Now I'll use a different color, something like this. Just see here. So I'll use a different color so that the diagram will not be disturbed. Now I'm taking this particle. Okay, yellow. It's actually okay. So now take this crust and this crust. So these two are the particles which are the nearest particles which are in phase, because there is no other crust here in between. So these two are the nearest particles which are actually in phase at exactly the centers of the two crests. Now what is the distance between them? What is this distance between them? Just observe. Now from here to here, one full trough is present really, and two half crests are present. Just see here, right side of this, right half of this crest and left half of this crest are present. So right half and left half together will make up one full crest. So what, how much part of the wave is present here between these two points which are located at the centers of the crest? One full trough is there, one full crest. What is one full trough and crest? It's nothing but one wave. It's nothing but wavelength. So even this also is coming to be wavelength. So this is very simple. So this gives another simple definition of wavelength. It is the distance between two successive crests. Successive means nearest crests, one after the other. Immediately, one follows the other immediately. That's called successive crest. For example, if you take this crest, this is alternating crest, this crest, and leaving the middle crest, the next crest is called alternating crest. So successive crest means nearest crest, which come one after the other immediately. So the distance between two successive crests is also coming to be equal to wavelength. The same way, even if we take the distance between two successive troughs, that also will come to be equal to wavelength, because that also can be proved to be consisting of one full wave. So thus we are getting one more definition. And what about particles? In terms of particles, the definition of wavelength. So this is a very accurate definition, very powerful definition, as important as this definition. Distance traveled by a wave in one time period is called as, we have seen that it's wavelength. Now we can get one more definition here. Just here, wavelength is the distance between two nearest particles which are in phase. You see here, which are in phase. In phase means something like in similar states of vibration, which are in phase or which are in the same state of vibration. So that is giving another definition of wavelength. So thus we have many definitions. So I'm not writing all those definitions because they'll be coming more clearly in other lessons, either this year or next year they'll be coming. Now it is actually not required. So only one definition I'm writing here. So only later I said I'll be putting the exact running notes at the in the last 1 or 2 minutes of this particular class. I'll be putting in the running notes. I'll write at least one or two definitions clearly. Now I'm not writing this. Even this also I'll be actually removing. Even this whatever I have written in yellow color, different color, for the sake of understanding, all that I'll remove, so that diagram will be very simple. So that's the new another definition for wavelength. So whatever things we are seeing here are simple. So nowhere any complication is there. So I'm again removing back all these extra things. So any doubt is there, just if any point you have any question, try to play back this video, only this particular 1 minute explanation, 1 or 2 minutes explanation, only just play back. That will be sufficient. Later if you want to write this, if you feel any point is very important, you require later, then you draw this roughly in the rough column with a pencil. You can draw it in the rough column when you get the printout, or when you're copying this in your notebook, there in the drawer of column and write this extra point. So later I'll be removing it. It takes some more time to remove it, so I'll not remove it now. So this also I'll remove it. So I'll keep the notes very neat. So that's about the other definition for wavelength. So next very simple thing is wave velocity. It's also called as wave speed, because the symbol for wave velocity is simply v. The regular symbol for velocity of any object is what? V. The same symbol is used even for wave velocity also. Now, why velocity and speed, the same name is two different words are used? The reason is speed can be proved to be the magnitude of velocity. Very easily, speed can be proved to be the magnitude of velocity is 30 meters per second. Velocity means direction also is important. 30 meters per second towards north or towards east. But without considering the direction, only magnitude will be 30 meters per second. That is nothing but wave speed. Exactly, it can be proved to be. That's why wave velocity is sometimes called as wave speed or speed of the wave or velocity of the wave. So it's nothing but velocity or speed with which the wave is traveling. How velocity or speed is defined? Distance traveled in 1 second or distance traveled in unit time. That is how speed is or velocity is defined. Or more accurately, velocity is not just defined as a distance but displacement, because velocity is a vector. Quantity similar to distance is velocity. Quantity similar to distance, but vector quantity is displacement. So velocity is defined in terms of displacement actually. Because same quantity, magnitude only is important here for wave velocity. Direction is not important. That's why it can also be called as here for waves, especially it can also be called as wave velocity or wave speed. Even light waves is even more important. Light waves, the quickness with which a light wave travels is called as velocity of light or speed of light. Their velocity of light, later in, you'll be learning that velocity of light really, though velocity is a vector quantity, velocity of light is not a vector quantity. It is really not a vector quantity. The reason is vectors obey parallelogram law of vector addition. Only velocities all velocities of all objects obey parallelogram law of vector addition. Only velocity of light doesn't obey parallelogram law of vector addition. It is just a scalar quantity. Velocity of light will never obey parallelogram law of vector addition. That's why it's taken as a scalar quantity, though it has magnitude and direction. So this was actually proved and very much used by a very powerful scientist, as powerful as Newton. Scientist was Einstein. In his theory of relativity, he explained this. Velocity of light is a constant. When uh, when something is given two velocities at the same time, two velocities of light in two different directions, what is the resultant velocity? We use parallelogram law. That is never obeyed by velocity of light. That's why it's considered as scalar quantity. So later in higher other classes, we'll be learning this more clearly. So distance traveled by a wave. Distance, what is speed of any object or velocity of any object? Simply distance traveled in unit time. The same way wave speed is also defined. Distance traveled by a wave in 1 unit time or 1 second. So whatever things we are seeing here are very simple. Nowhere any complication is there. Now just observe here. Unit time means it's nothing but usually second it's taken. Now even frequency also, number of vibrations in 1 second means what is the meaning? In 1 unit time. So we use unit of time in general as second only, but sometimes even other units per minute, per hour, in 1 hour, like that, such big units also can be used. So that's a more general definition. Number of vibrations in 1 second, it's simply more general definition for frequency is number of vibrations in unit time. But most practical unit is only second only, for especially for measuring frequency. Only when it's measured in seconds only, we express the unit as vibration per second or vibration per, more general will be vibration per unit time. When it is vibration per second, that only is called as hertz. So when the unit is vibration per second, then only it's called as hertz. So vibration per minute means it's not hertz. It's not given any name because it's less useful. Because it's widely used, it's called given a single word name. Just as widely used unit of force kilograms meters per second square. Simple one single letter, single word name is given Newton, like that. So distance traveled by wave in unit time is called as wave velocity. So what is the equation for wave velocity or wave speed? Regular equation for wave speed or speed of any object is what? Distance by time. The same equation is used, distance by time or d by t. So this is a simple thing related to wave velocity or wave speed. So these are the main quantities related to wave motion. So out of the 5 quantities, usually 1 or 2 quantities are given in the board exam. So that way they are very very important. So two definitions are given, is definitely it carries minimum 4 marks, and all the definitions are very very useful for solving different models of problems, and they are very very useful in different derivations. So just see, they are very very simple, each and every definitely just 1 or 2 lines, very easily they can be remembered also. So that's the thing related to the present topic, that is quantities related to wave motion. Now I said all these 5 different quantities related directly we are obtaining all of them from what? From this simple formation of wave. From this simple diagram only almost everything we got. Now it has still further uses. So the next is again, it's even smaller than this quantities related to wave motion, but carries even more marks than this. It's a very short answer question mostly. So two definitions given 4 marks. Only one is given just 2 marks. But the next topic is actually on almost essay question already I said, but it takes only 1 minute or 2 minutes for the entire answer. Directly by using the diagram, we can get the entire answer, entire derivation. So what is this? So it's called relation between frequency n and time period t. So this is actually a 3 marks answer, strictly speaking. So it doesn't take much time. And next topic is the real topic, most powerful, most important equation related to wave motion. Relation between velocity, frequency, and wavelength of a wave. So directly using the definition of a wavelength, it comes just in 2 steps. So this is the 4 marks answer. So it carries around 4 to 3 marks. Sometimes it's given only for 3 marks. Sometimes usually it's the 4 marks answer. So now considering the relation between frequency n and time period t. Now first consider the definition of time period. So what is the definition of time period? So from the definition of time period is the time taken for one vibration. So from the definition, so what is the definition of time period? Time taken for one vibration. So from this we can say that, so this is the definition of time period. So time taken for one vibration itself is the time period. So this is nothing but what? Time taken for one vibration is t. So in units, what are the units of time period? Usually seconds. So we can just say that it's t seconds. It can be 5 seconds, 4 seconds. In general, it's taken as t seconds. So this is the time taken for one vibration. Call it as equation 1. Now apply the definition of frequency. What is the definition of frequency? It is the number of vibrations in 1 second. So simply number of vibrations in 1 second or 1 unit time. Exactly speaking, 1 unit time. But usually we measure the frequency, we measure time only in general related to wave motion in seconds only. So number of vibrations in 1 second. Now from this, what can be said? What is the time taken for one vibration? It's t seconds. So what is the time taken for n vibrations? So number of vibrations in 1 second. So frequency is n, means n vibrations are made in 1 second. So time taken, just observe this, it's very simple. Number of vibrations in 1 second itself is called as frequency. Frequency is n vibrations per second, means n vibrations are made in 1 second. So time taken. So we are not using anything more than the definition. So here we are using the definition of time period. Now next, from that we got equation 1. Next, definition of frequency. Number of vibrations in 1 second. So time taken, number of vibrations made in 1 second itself is called as frequency. Frequency is n vibrations per second, or n hertz, means n hertz simply means n vibrations per second. That means n vibrations are made in 1 second. So time taken for n vibrations is what? Simply 1 second. But this can also be written like this. So call this as equation 2. So now, what is the time taken for one vibration? T seconds. Next vibration again, next one vibration, time taken will be again another t seconds. So what is the time taken for 2 vibrations? T plus t. Observe this, it's very simple. Time taken for one vibration is t seconds. Next one vibration again it takes t seconds. So time taken for 2 vibrations is t plus t, 2t seconds. Time taken for 3 vibrations will be 3t seconds, t plus t plus t, 3t seconds. Time taken for n vibrations can be written as what? N times t seconds. So directly from equation 1 we can get. So time taken for n vibrations can also be written as what? N time t seconds. What is the reason for this? Time taken for n vibrations is n times time for one vibration. What is the time for one vibration? T seconds. So it is n times t seconds. So call this as equation 3. Now just apply to equation 2 and 3. So time so what is equation 2 here? This here, time taken for n vibrations in 1 second. The same time taken for n vibrations can be written as n into t seconds. So both are nothing but time for n vibrations. Time taken for n vibrations in 1 second, that's also nothing but what? N into t seconds. So we can equate both of them. So any doubt here? Just check it. It's not complicated. Nowhere it's difficult. So first we got the equation 1. Using that equation 1 only, we got some time for one vibration we substituted. And we got n into t seconds. This is why we are getting this step. Since equation 1, just see here, we're getting this step. So now what we got is time taken for n vibrations from the definition of frequency is exactly 1 second. But from the definition of time period, it is also equal to what? N into t seconds. So both are one and the same time taken for n. So we can just equate we can just equate 2 and 3. So 2 and 3 implies what? 1 second is equal to n into t seconds. So no complication here, no doubt here. Any doubt is there, just check these two steps once again. Just how the definitions are applied, just check it. It will become clear. So 1 second is n into t seconds. So ignore the unit second. 1 is what? So cancel off. We can just ignore. So 5 seconds is equal to a seconds is 5 seconds means what? A is an unknown time. 5 seconds means what? A is equal to 5. So we are just ignoring the units. Something like cancelling of the units like that. So only rough I am just showing this. Any doubt is there, such rough work will be very, very helpful. A seconds unknown time is equal to 5 seconds means what is A? A is nothing but 5. The same way 1 second is equal to n into t seconds means 1 is equal to n into t. So therefore you take t to this side, we are getting a simple relation between frequency and time period. N is equal to 1 by t. So this is the relation between frequency and time period. How are they related? They are inversely related. So if time period is more, time period increases, frequency decreases. So they are said to be inversely related. So this is also written as n is inversely proportional to t. So this is the proof for why frequency and time period are inversely related. The higher the time period, lesser is the frequency. The lesser the time period is very, very less means frequency will be very, very high. It is easy to understand. Time period means time taken for one vibration is very less. So time taken for one vibration is very less means fast vibrations are taking place. So in 1 second, more number of vibrations. That means frequency n will be more. That way the equation can be understood. So this is a very, very, very important relation between frequency and time period. So in how many steps it's coming? So just in 2 main steps. Time taken for one vibration is t seconds, and from the definition of frequency, time taken for n vibrations is 1 second. So but time taken for n vibrations is what? N into time taken for one vibration. But time taken for one vibration by definition of time period already we got t. So n into t seconds we are writing. So 1 second can also be written as what? N into t seconds. Just check it once again. So that means n into t is equal to 1. So n is equal to 1 by t. So nowhere any complication is there in the derivation. So whatever things we are seeing here are simple, nowhere any complication is there. So this is a simple derivation of the relation between frequency and time period. Now next is the relation between velocity, frequency and wavelength. Though it's carrying 4 marks, it's actually the simplest of all the topics which we have seen till now. Now what is the definition of wavelength? Now directly apply the definition of wavelength. So from definition of wavelength. So what is the, how is wavelength defined? It is the distance traveled by a wave in one time period. So in one time period, how much distance the disturbance or wave has traveled in the medium? Just see, in the medium means in the string, exactly equal to wavelength. So from the definition of wavelength, lambda wavelength is the distance traveled. Always while deriving the relations, whether this relation or the previous relation, first we have to state the definition, and from the definition we have to get the next steps. Lambda is the distance traveled by a wave in how much time? In one time period. In one time period. So from the definition, what we get is, we get a very simple thing. What is the distance traveled in time of one time period? It's equal to lambda. So distance traveled in time t seconds is equal to what? It's nothing but lambda. Call this as equation 1. So now we require a relation between velocity, frequency and wavelength. Now what is wave velocity or wave speed? So now apply the definition of wave speed. So wave speed is what? It's the distance traveled in unit time or simply speed of the wave. So using wave speed or velocity equation. What is the equation for any speed or velocity? It's nothing but distance by time. Now this equation for speed or velocity, so we are now mainly considering speed. For a wave, speed and velocity are considered to be same because direction is not important. Direction of motion. And for example, for light waves, it is not even more less important. The difference between scalar direction and that is scalar and vector quantities, because wave velocity for light waves is complete scalar quantity. Even for other waves also, direction is not considered to be much important, though they are actually really vector quantities. All the other waves velocities are nothing but vector quantities. Only for velocity, only for light only, velocity of light is a scalar quantity. It's not a vector quantity. So now considering the regular equation for wave speed or velocity is distance by time, which can be written as d by t. Now apply this in the definition. So in a time equal to t seconds, what is the distance traveled? It's nothing but lambda. So in when time, so from 1, what we are getting, call this equation as 2. So from 1, when time of travel is exactly t seconds, what is the distance traveled? Exactly equal to wavelength from 1. So substituting these two, any time interval corresponding distance, divide the two, will get the speed of the wave. So in this particular time interval equal to time period, the distance traveled is exactly equal to wavelength. So substituting these two here, we can get the velocity. So therefore, what is the velocity now? Simply in place of d, it's lambda. So lambda by t. So this is called as the first result of the derivation. But still, you see this here, we got only relation between velocity, lambda, wavelength and time period. Velocity, wavelength and time period. V is equal to lambda by t. It's almost looking like a distance by time. In place of distance, we have wavelength. In place of time, we have time period. So it's not difficult to remember. Just like it's looking like almost like regular equation for speed or velocity, distance by time. So this is also not difficult to remember, but it's not much important. It's not considered to be much important. So it has a lot of meaning. The distance traveled in one time period is what? Wavelength. So a lot of meaning is there in the equation, but still it's not considered to be much useful. So very useful equation is this one. So this in the mid next step. So V, N and lambda, or V lambda and N. So here what we have? V lambda and T. So in place of T, if we put N, we'll get V lambda and N. The required relation we'll be getting. So this can be obtained in the next step. Write it as simply 1 by T into lambda. And what is 1 by T? What is 1 by T? Frequency. Already we have seen this. So but frequency is what? 1 by T. Now, substituting this here, in place of 1 by t we can put n, therefore what we get? V is equal to n lambda. So this is a very popular equation related to any wave. Any wave velocity can be expressed is nothing but equal to what? Product of frequency and wavelength. It's a very important equation. So most important equation for waves, especially for propagation of a wave. So this is the main result that's actually required. See here, it's carrying an entire 4 marks, but how many steps it's coming? Just one main step, the definition of wavelength, directly applying it in the velocity. Almost in the next, we are getting in the next half step, we are getting the result. So this is not a big thing. Once we are getting d by t, lambda by t, it's almost not like a big separate step. And 1 by t, we know its frequency. Almost in the next half step, we are getting the required answer. Just in 2 or 1.5 main steps, we are getting the entire answer. So simple they are. So that's about the two simple derivations based on the wave motion. So whatever things we are seeing here are simple. So now already I said this entire notes I'm just fairing it, and now in the next moment I'm displaying the notes you have to take the printouts, and from the printouts very easily the answers, the topics can be studied. This is the running notes which I said I'll be giving at the in the last 2 minutes of the class. So this is the first page, page one, like that. 4 pages it's coming to. So all these 4 pages directly I am giving the link at the title of the video in the channel of this particular class, board class video. So from the link you can directly download all the 4 pages. Just for convenience I'm just explaining this a little for half minute or so. This is the left side of the page 1. So top to bottom I'm showing. So next right side page. So I have provided this clearly, learn only the definition. So only the definition should be learned here. Only the definition should be learned here. So explanation only for the sake of understanding. Once you have to read the explanation, that's sufficient. So next just see the page 2. So this is the explanation of the for the wave or wave motion. Definition is in the previous page. So this is a complete explanation. Only once you have to read. Same as I have explained in the class. Next on the right side you see quantities related to wave motion. This is a page 2. Next page 3. So continuation of the quantities related to wave motion. So 5 quantities it's coming to. Next page 4. Page 4, 2 derivations are there. They are simple. So because they carry 3 marks to 4 marks, entire derivation should be learned. They are very simple steps directly based on the definitions. Just by learning definitions, everything becomes very simple. Definitions are obtained from where? Already we have seen, always in science and technology definitions are always obtained from the real life situation. What is the real life situation? Formation of the wave. Already we have seen how the wave is formed. From that only definitions are obtained. From the definitions, derivations will be actually based upon. That's always applicable to every topic in science and technology or science and engineering. So download the pages, that's the best way. Those who don't want to download it, just copy down the entire topics, all the topics in the notebook or in the class workbook. So that so once a class is listened to, second time you should not listen to the class because it's class will be very lengthy. Due to complete explanation, it will be very lengthy. Only once you have to listen. But always how to be always ready to solve any kind of problem or ready to answer any kind of question. Every day you should be revising that. What should be revised every day? Your material, your notes should be revised. So the most important things in the notes is definitions and derivations. They have to be revised regularly, almost every day according to your convenience. So for that reason you have to keep the notes ready.